The first presentation. So I have uploaded all of them. Yeah. If
James killed the section about.
James did. Okay, so I'll take care of this. Yeah.
Okay, so if you have it, then please upload the first one. Then upload it on the other one.
Okay, so yeah, I do it. I didn't take that into account. Sorry about this. Because I uploaded them from the hotel, obviously. When the session was like available or has become available, and then I didn't realize that James.
Well, if you have that one, sensor segregation.
Yeah, I do, but I cannot find the other ones as well.
Well, they're all there now, except for that one, because that one was not in Indigo.
So for some reason, okay.
I downloaded all these.
Yeah.
With demos.
That's interesting. Either like from there.
You got it from here?
No, from the other. So when you go to the contributions list, and then
Really?
yeah, I was like,
Hey, Rafael, can you hear me? Hello, this is Ray online.
yeah, that can be a little later. So the first
Oh, you can leave it on that one, I think.
Alright, so
Okay.
which user is like logging from this? Oh, you can take it.
Yeah.
Yeah, if I want to, it's because it's not clear to me. If I want to leave the session, can I just close this tab or is it the way?
They're up here on this menu item.
Okay.
There's the. Ooh, don't mess the bottom.
Yeah. They're just too close to each other.
Yes. Yeah.
All right, I'll do the speed setting during the break.
Okay.
Yeah.
Yeah.
Thank you.
Yeah, sure. Sorry.
Yeah,
I'm fine. How are you?
you made it.
You made it, yeah.
Let all of us what happened. So.
Yeah. Bad.
But yeah.
Okay.
Really bad.
How you doing now? How are you? Good.
Okay. Yeah, I'm sure. Great. Oh, okay. So, okay, I will be giving a short intro, so I. Right. Ready? Awesome. All right. So, hello, everyone. So, welcome. Thanks for coming. This is the thermal control and power management session. Let me first thank our sponsors who made it possible for us to meet here. So thank you. Also, I'd like to thank the organizers for their effort, because without them it wouldn't have happened. And the short organizational announcement. So we have the mics. They are throwable, but if you use them, please stand up so the camera can catch you. And yeah, and because we have remote participants, please always use a microphone when you speak. So that's it. So that's basically all as a matter of introduction. So I'm going to give the floor to Daniel now. Or if I don't know if
Yeah, I'm gonna be I'm the room shepherd, so I'll be the microphone runner.
oh, okay. So the Alexander is going to present, or you are going to present? Okay, so please come over here, and I will pick up the hopefully. All right, so the floor is yours.
Hi. So I'm here to talk about the thermal aggregation. So first, why we need it? Do you have to change the slide? Oh, okay. At the beginning, I started to write the thermal aggregation for MediaTek for one of their drivers. But actually, I don't think we need it for MediaTek. They used it, the thermal aggregation, as a workaround for a driver that was not correctly written. And today, I'm not sure that we still need it for MediaTek. So it's all done. I can go back to home. No. Another options, another need we could have maybe the IPA, the power allocator governor. So one usage we could have with that would be to feed to drive the PIT loop. So that one use case we could have with thermal aggregation. I would be curious if in the room there is maybe some people that will need the aggregation and that would have some use case for it. I guess that's no.
Wait. Sorry. If you can stand up.
Oh, yeah, sorry. I don't know. I don't know what aggregation totally means. Do you mean that, like we have virtual sensors, which is nothing but X, Y,
Yes,
some
we
quadratic
have
dependent
multiple
equation.
sensors, and we wanted to aggregate the temperature and other values to get one virtual thermal zone from those sensors.
Okay, yeah, it's okay. We do, yes.
Okay. So that's something that would be useful for you?
Yes, definitely, yeah.
For
But-
kind of use case for the power allocator governor or for another use case?
Yeah, I didn't look at your full, how you're proposing, but in general, the way our virtual sensor works, it's not just sensor aggregation, but it also has inputs from other subsystem. Like you have one CPU sensor, for example, but you want to interpolate what my skin is, temperature would be.
Yeah.
So that in sensor plus one, maybe some other sensor, but they don't have sensor on the skin. So that plus your CPU utilization and what parts are closer to that.
Okay.
So it's also an equation. So it's not just sensor aggregation, sensor plus other inputs you can get.
So initially, when I did the aggregation, it was for one specific use case of Minetech, which was getting the maximum temperature of the SoC. So it was taking all the sensors and was extracted the maximum value. The proposal I made was not generic enough. It was just for device tree. So the new one I would like to introduce will be more generic and will be usable with device tree and CSFS and eventually CPI. I don't have any knowledge about the CPI, but I think it should be feasible. The idea is to create a new thermal zone from other existing thermal zone. So if we take a CPU, we can have one thermal zone for each CPU thermal sensor and create a new virtual new thermal zone that will aggregate all the CPU temperatures to provide a new one.
So I don't know, Rafael, we have time to talk now or discuss because you have a short time? Or
Let's continue on this topic. So we are like 7.
7 minutes.
But if you have
Yeah, so like here, I'm still having issue with thermal zone as aggregator, right? Your DTU has a thermal sensor, right? Why don't you call thermal sensor? Why you call it zone, right? Zone itself has cooling devices and other things, right? Sensor is aggregation of sensors.
well, well,
Maybe just to clarify, the idea is to aggregate the sensors inside the thermal zone. So you don't aggregate thermal zones, you aggregate sensors. So you in the description, because well, in the device tree, for example, we have the thermal zone, and you point to the hardware, the sensor, and you can put several sensors for the same thermal zone and saying, okay, we will use the maximum, the average, or whatever. For the DT, we already have the binding, but it's never implemented. So yeah, it's not about aggregating thermal zones.
But can I see from user space what sensors segregated? No, right? That's what. So
Create one thermal zone, doing the aggregation of all these sensors, and you can create per sensor a new thermal zone. So
yeah. But the point is that Srinivas would like to, Srinivas would like to know which sensors are involved in the aggregation. If this is an aggregate.
why do you need this information?
Well, because user space may need it, like for some computations or debug or something. Yeah, it's not an unuseful piece of information, in my opinion.
You can put that in debugfs.
Yeah, debugfs or even in sysfs if this is an aggregate zone. Just because it is good to know that it is aggregate and not a like sensor related or sensor attached thermal zone. So so you know that the temperature is not doesn't come from the sensor directly, right?
When it breaks, you want to find out why.
When it's broken, you need to know its components to find out, was the math broken or is one of the subsensors broken, right?
Yeah, okay.
I don't know if this one's working. A little bit, yeah.
So the idea was to create a new thermal zone and that work as any other thermal zone. So we could eventually, if that makes sense, bind the cooling device to this aggregated thermal zone and do any other use case we do with other real hardware thermal zone. I made two proposals about it. The first one was to create some kind of driver that was taking the virtual zone and doing regression. It was rejected, and the second one was more close to be accepted. One thing that was blocking was some rework to do in the thermal framework. So I'm here now to try to rework this last proposition and to make it accepted. One thing that was also not good was I was only focusing on the device tree. So the next patch set will fix that. So the idea will be to create a generic new file to do the aggregations. So why I'd like to avoid to just doing modifying the current functions to avoid increasing the compute time of the thermal functions. So I would like to propose a new set of functions that could be used instead of the regular one if we need to do some aggregation. So I'd like to implement it using the existing device tree bindings. This has been lost, but before we move to the YAML format, there was some discussion of the aggregations. Actually, it was called multiple sensors, and there were some kind of mathematical data to compute the value of the sensors. So the idea would be to use the same what already exists, use it, and eventually add also some other aggregation functions such as the maximum or minimum value, if that makes sense and if it could be useful. There is a couple of things that make it still difficult to implement. Currently, if we want to do some aggregation, we still have to call the vendor operations functions to get the value and to use the average of time to compute the new sensor value. Yeah, as I said, I would like to avoid to do a lot of computation for a simple sensor. We don't need to have all the aggregations done if we only have one sensor. And the way to register a thermal zone is quite complex when we want to do multiple sensors. Basically, when we register that's the driver that registers the thermal zone, and basically it goes through device tree, register all the thermal zone defined in the device tree. And if we want to do a multiple sensor thermal zone, we don't have a driver or something existing for this multiple thermal sensor zone. So what I did was a kind of workaround to be able to register from the driver sensor thermal zone. I was How to explain that? I was registering the expected thermal zone as requested by the driver. And if there were another thermal zone using this sensor for multiple thermal sensor zone, I was also adding it to this virtual to this multiple sensor thermal zone. So that's clear. That's all. So do you have a question? I think so.
So I'm assuming that this is intended for in-kernel consumers, because if it was outside the kernel, you could just run a script and aggregate those temperatures outside. So do you have a specific use case in mind? I understand things more if I know one of the use cases or a couple of use cases.
One of the first use case coming in mind is, for example, you want to use the power allocator, the IPA, to mitigate the CPU. So if you have multiple sensors, which one you will choose to mitigate? Because you have the IPA will be dealing with the cooling devices, the same cooling device. So you can aggregate the cooling devices decision in the thermal framework directly, but the IPA is not inclined to work with several instances.
Mm-hmm.
So by aggregating all the sensors into the same thermal zone, you can use a single governor to manage all the CPUs.
But then you have to bind your cooling devices to the thermal zone as well, right?
Right.
Okay.
I have a question on the remote.
On remote? Okay. Lucas, yeah.
Yeah. Hi, guys. Can you hear me?
Yes.
Okay. Yeah, this is Lukasz Luba speaking, the IPA maintainer. So this looks like a really nice feature if you could do this multi-sensor thermal zone kind of stuff. Because currently, if you have, let's say, one sensor per CPU plus GPU, and IPA works only with thermal zone with one sensor, and let's say this is SoC sensor, then you cannot react properly for hotspot on one of those CPUs, for instance. And if there is a way to loop over all the sensors and at least get the maximum and figure out the hotspot, that would be really useful, because we have to split the power budget for the whole SoC, but actually in some safety boundaries, like avoiding the hotspot temperature issue. So this would be one of the use cases, which is, for instance, there are some already existing boards which don't have that support, and IPA doesn't work well on them at mainline, and they are mainline boards.
Okay, thanks for the comment.
I'm not sure that it's a good thing if we aggregate sensors if they are not tied together in the same performance domain. Otherwise, we will end up having a...
Well, so that's why Srinivas wanted to have the information about which are involved, right?
Right.
Because then if you know that, then you can take that into account. All right, I think that we need to move to the next topic. So let's move the conversation to my English and so on going forward. So thank you.
So how do you change the... so the title initially of this presentation was different tree types, but actually what happened is we merge different subjects. So these subjects are merged into a single presentation, and we will I will present three different things I do believe it makes sense to implement the thermal framework. So the first one is the trip point. So what we have today is a lot of hack in the kernel because user space is interested in receiving information about when we cross the specific threshold. So the thermal framework is used to monitor the temperature of a specific device, and they rely on the interrupt mechanism of the sensor to get information. So in order to do that, so yeah, they track the temperature. They don't want to track the temperature to protect the silicon, but they want to track the temperature to know exactly what is the thermal situation of the system and act on different places in order to reduce the power and fulfill skin temperature stuff and constraint and so on. So for that, the kernel is providing an option which is called the writable trip points, and that results of having an user space. You can write these trip points and change the critical trip point, the hot trip point, passive trip point. So you can change actually the configuration set by the firmware, and that's not a good thing from my point of view. So the proposal is to introduce a new trip point, which could be called, for example, user trip point. So we can clearly identify that this trip point is for user space. So we keep using the logic inside the thermal framework. It will be handling the trip point and setting threshold and interrupt when we cross specific temperature with this trip point. But as it is a user trip point, we do nothing else than sending a notification to user space. So with that, we should be to have this trip point to be writable and disable the option in the kernel where we can change the trip point in sysfs. So the question is, shall we be able to create several trip points? Does it make sense to create these user trip points?
So one question is about the interrupt. Based on the interrupt signaling of the crossing, right? So that in order to do that, the hardware or firmware needs to know that the trip points exists, right? In order to send an interrupt signaling the crossing of a trip point,
yes,
the hardware needs to know that the trip point actually exists.
So when you cross the trip point, the framework.
Yeah, but I know that. But to get an interrupt from hardware, you have to tell the hardware that there is a trip point for which it should generate an interrupt, right? Because otherwise it won't do that.
Yes.
So with the user trip point, the hardware has to be able to. There needs to be a way to program the hardware, right? For this. So right. there is a requirement. So you cannot create that for any type of a sensor, for example, which is not programmable. Say.
Yeah, it will be monitoring.
Yep. So you need to use polling then, right?
Yes.
Yeah. Okay.
So it's basically you keep the existing mechanism. It's just you create this new trip point and do nothing except send notification and rely on all the mechanism of programming the next trip point, the previous trip point.
So we do use passive trip points, like if you look at our drivers, we do misuse one of the trip points.
So you have to enable the writable trip point.
Yes, we
create passive trip points and you use them from user space.
Yes, that's what we do. Yeah. What Rafael asking, I think in that case, if there is no driver who can program hardware, you should not even create it, because it's for me, having more entries in the sysfs is a problematic because we have to search for them. So if suppose your hardware is not capable to give you interrupt, don't even create it.
Assuming the hardware can interrupt at an arbitrary temperature, I mean, do you could you support an arbitrary number of trip points by just programming whatever the next threshold is, up or down, once you reach a certain trip point?
Yeah, there'll be always hardware hysteresis, because by the time you read, actually the temperature might have already changed. So that's,
Yeah, but
so I'm saying that don't create if you hardware not supported.
if the hardware does not support it, we will rely on the polling mechanism.
So we will create a thread in your thermal CFS to poll.
No. We keep having the system, the thermal framework polling and watching the temperature of the thermal zone.
Yeah, so that's an overhead, right? Why to even create a polling? If you have to poll, user space can poll too.
Yeah, but it's
Right.
if you write a program and you want to get a notification, it's easier. You get the notification, whatever the mechanism you have in the kernel. If the kernel is, you set, if you have, if you don't have the interrupt supported by the sensor and you have passive 3 points, anyway, you have to activate the polling.
Yeah, the reason I'm saying, if you look at ACPI driver of Intel or whatever, you will see many polling threads create a number of zones. They are, because
so
you'll have 10 threads, 10 zones just sitting there, just wasting your thread space.
but anyway, so
Yeah.
if there is no interrupt, programming support in the sensor hardware, there is a little sense to create those user trip points, because the user space can pretty much monitor the temperature in a loop and and do whatever it likes. Then the kernel doesn't need to do that. So it's probably the only benefit would be to reduce overhead of entering and leaving the kernel then for the temperature readout. But that's it. Okay, we need to move to the next one, I guess, because time is running.
So next one is thermal debug FS. So we have very few information. So the thermal behavior on the system is something very complex. And even we cannot debug everything and profile everything, because it's not possible to do that from the kernel space, but we can at least give some information about how behave the kernel with the thermal. And so today we have very few information about how the thermal is behaving on the system. And on the other side, we have, we put some stats for the cooling devices. And there are bogus now, because we have a lot more and more states for the cooling devices. And because it's a matrix of number of cooling states multiplied by the number of cooling states, you can end up with several megabytes of memory used just to show basically an empty matrix, a matrix full of zero. And the CSFS there is a restriction where you cannot show more than one page size information. So from there, it's very hard to have a relevant information because it's truncated. So the idea is to provide something easier to debug. So we have so we have overshoots and undershoots. So that's two things we want to try to reduce as much as possible and stick to this temperature limit. Having the information about if we are doing a lot of overshoot or undershoot is interesting for us to know, for example, if the governor, the logic, if the configuration is good, and so on. So I sent the first RFC where we have basically something similar to what we have in CSFS. It's just a bit simplified. So you have the thermals under the kernel debug directory. You have the cooling devices, then the ID and data inside, and then you have the thermal zone, the same. You have ID and a mitigation file. In this mitigation file, it's a lot of numbers, but we have mitigation episodes. So that means every time we cross a 3 point, we begin to mitigate. We can cross several 3 points or not. And then when the full mitigation episode is finished, then we can account the time duration. We can account the average temperature, the minimum temperature, maximum temperature, and see from there at the first glance how it's behaving. Then after that, we can create under the mitigation, under this directory, a new directory called with the timestamp number representing the moment the mitigation episode began. And then inside we put more data like the speed temperature, average speed temperature, standard deviation for the average temperature, and so on.
All right. So this is in the list. This is on the list and as an RFC.
Yes,
so
right.
Anyone who wants to see the code, please do that. Send comments and so on. Okay.
Especially if there are specific data you want to record in the debug.fs.
And you already have a use for this data, right?
Yeah.
Yeah. Okay. So, yeah. Any comments to that? No. Yeah. Go ahead.
So the last topic is improving the stepwise governor or create a new governor. So the problem here with sometimes the stepwise governor does not react fast enough. So the consequences is we have overshoot and undershoot. And the current solution is to increase the sampling. So increasing the sampling, does not help to reduce the load on the system. So the idea is, let's imagine we can compute the temperature speed, and then we do an estimation, a guess estimate of when we will cross the temperature limit on the way up and the way down, and set a timer at this moment, and then take the decision from there. So in usual use case, what we have here, so we cross the temperature limit, we receive an interrupt, we do a decision saying, okay, +1 for the cooling state, then the temperature decrease. If there is the reaction because the interval is too high when we monitor the temperature, then we miss the moment we go below the temperature limit minus the hysteresis. So we have an end of mitigation, reduce the cooling state, and then we cross again the limit. And again, we increase the cooling device state. Temperature is reducing. Then hopefully we catch before we reach the hysteresis -0. We decrease the cooling state and so on. And we have this wave. The perfect mitigation would be having a flat line just on the limit. The proposal is to use the slope of the increase of the temperature to do a computation and detect when we will cross the limit. So instead of having the temperature limit I being the temperature limit, we have a temperature limit I and the temperature limit low, and in the middle we put the temperature limit we are aiming to mitigate. So from there we do forecast, we try to predict when we will reach this temperature limit, and we set a timer at this moment. So basically that's the idea. There is no experiments yet.
So what is the approximate time base there? Because these kernel timers, they're not an exact science. You can ask for a wake up at a certain time, but it will depend on what else the kernel is doing, right? So is it seconds? Is it milliseconds? Is it fractions of milliseconds?
It's milliseconds.
Yeah, you'd have to find out what the resolution is of those timers.
Yes, that's the difficult part. But of course, there is one moment the thermal stuff cannot be handled by the kernel. If the transitions are too fast and changing too much, then you need to be assisted by some coprocessor, power management coprocessor outside taking care of that because you cannot do that from the kernel. But that there is one point. You say that we have to react fastly if the CPU is doing something. I do believe the thread doing the polling is actually like any task. And we should change that to have a real-time task or something like that.
Yeah, it might have some serious power consequences
Maybe.
to do
Yeah,
that.
yeah.
If you have a sensor with an interrupt, you could like program the interrupt on the boundary, I
Yes,
guess.
yes. That works only on interrupt-based sensors. Because what we want to do is to prevent having to be delayed by this monitoring. Just adapt depending on the speed of the changes and transition.
Mhm.
We adapt and set timers so we can react not a posteriori but a priori. So
Got it.
before.
Thank you.
But if you use the interrupt, you already consumed user, usually hardware will have one trip program. If you use hardware to give you interrupt, you basically use the user space trip, right?
No.
Like instead of polling, you set the temperature to that limit.
Yes.
Into the informed hardware to give me interrupt. Hardware usually have one threshold to give
So
you.
I guess you mean that if this is used, then user trips
Are not used. Yeah.
Couldn't be used, right?
Why?
User trip points couldn't be used along with this mechanism if you use interrupts. The signal.
The trip points is a lot below. So when you use the interrupt and you cross the trip point, the thermal framework will program the register for the next temperature.
So you have to keep the user space, whatever user trip user space wanted to get in somewhere, so that you are programming.
I'm not sure I get the point.
No. So you want to use the interrupt from the hardware sensor.
Yes.
Both for driving the stepwise governor and user trip points, right? Because they also would need the interrupt. And now, what if there is only one that you can program? So.
Yeah, I understand now. I understand.
Yeah.
So you see, we should end up
Saving.
having a conflict.
Yes.
Because user space can do the changes. Yeah, so that's a conflict. Yeah, good point.
Yeah, and even if without the user trip point, you have in this diagram trips at two different temperatures.
Yes.
So either you need two interrupts or you have to change the interrupt. But what if you overshoot by the time you've programmed, the interrupt from limit low to limit? Like, how do you handle that case?
I don't know.
It's the same thing as trying to use one interrupt to handle the user trip point moving around.
Yeah.
It looks similar like a PID controller, PID controller. So
no, it's not similar because the PID is based on regular intervals.
Oh, so it's not constant.
Monitoring.
Okay.
So it's like, and it's because we have this regular interval that we can doing the math. It's based on these intervals.
So it's not enough to estimate a rough interval for sampling, basically.
Yeah, I don't know. It's the PID.
Because you could implement that in kernel and provide in user space the coefficients basically for proportional integrate and derivative.
Yeah.
And then based on each platform, somebody would come with the transfer function, I don't think it's called, where they would measure and would say, okay, this is what you need for this specific platform.
Yes.
And then you don't have the overshoot, you don't have the undershoot. Well, you have, but it's limited to.
Yeah, right. So that's an idea we have to try. It's not implemented, and then when it's implemented, we can compare with the PID. And just to mention that you were talking about the coefficient. Lucas has an algorithm to automatically, given the overshoot and undershoot, adjust this coefficient. So we are thinking about how we can do that. So we don't want to put all the math in the kernel to compute this this coefficient calibration, but we are thinking about something communication between user space and kernel space. So the user space can give new coefficient depending on what the kernel space say. Oh, okay, we are in this situation. We are behaving like that. So
How many coefficients are there? It's just one from the Lucas formula or whatever.
I think it's 3 coefficients.
Okay, okay. So maybe it's the
undershoot, overshoot, and another one. Don't remember.
Okay, okay.
Yeah, thanks. Yeah, so there are 4. Maybe slightly not to this slide, but for this debugfs. So I hope that this debugfs could be writable. So we could actually force the learning algorithm for IPA. So you can actually allow for some optimization method, and that would give you as an output, maybe also with this debugfs, some possible good coefficients. So, but let's discuss that on this part set the RFC, this debugfs.
Okay, okay. Thanks.
All right. So we need to switch topics now. So thank you. Srinivas.
Thank you.
I just slide. This thermal. It's just page up, page down. Right. You're
Good afternoon. My name is Srinivas Pandrivada, and I work for Intel, and I contribute to thermal subsystem from last decade. So as Daniel mentioned, user space is also a participant in thermal management. In a long time back, everything was in kernel, but user space has lots of new things because of systems getting smarter. You need more user space involvement. And one of the AVI we use is Netlink. To give you a very high level overview of Netlink, Netlink is one of the user-kernel communication mechanism which we have in kernel. And also it can be used for user-to-user based. It's a socket-based, it's a data game-oriented service. And you can do both unicast and multicast. And we have Netlink, Netlink has families. And we have primarily 2 of the families are getting used. One is Netlink K-Object U event, which is used by user space governor, I don't know, maybe from decade plus. And Netlink generic, Daniel introduced in maybe 2-3 years back. And Netlink generic is also used by ACPI thermal events, maybe more than a decade is there. So we have a combination of user space notification mechanism. To give you, like how it's a usage model on Intel platforms, you have like from a driver perspective, you have in the thermal core, the driver just calls one API, device update or any other mechanism, and the thermal core based on what policies for set for that thermal zone calls if user space is set, then it calls to user space governor, and user space governor use K object U event, and it's basically string based format. Send it to any K object U event will be intercepted by UWD and any other applications at the same time. And similarly, thermal core can also call thermal netlink, and the thermal netlink uses the generic thermal generic netlink generic, and it also can send the user space using different mechanisms. So we have combination of mechanism, like in addition we have ACPI thermal If a threshold change comes, you get many events now. So you can also get from ACPI thermal. So in like we are looking for user kernel interface. We want really it to be low overhead. It's a low usage of resources because it's a communication mechanism. It shouldn't be take more than what it should do, and it should be fast enough to mitigate thermals. Like 5 years back, yeah, those time frames were okay, but as more active devices sit in your laptop, yeah, those gets challenging. Like we were talking about undershoot, overshoots. Those needs to be mitigated fast enough. So recently, like user space governor served its purpose, but as we have more CPUs and more, like more smarter things, we see that you can really freeze the user space. So you can just send events in a group, and it will locally freeze the user space. And if you look at one of the user complaints that this system basically takes 100 MB of memory by just because of this UWP. And why this now? Because previously you had 4 CPUs, now you're talking about 32, 64, or whatever number of CPUs. They all contribute. And if you look at UWP algorithm, it spawns many workers, and the workers are proportional to the number of CPUs. So the moment you see the event, it just spawns. And most of the time, it's a problem in the firmware. They send the drift so bad that it gets constantly violated. And also, like we said, when you program interrupt, you can say that how fast you want to generate interrupt. And if it's not programmed right, it just at the boot up, you may get 100 events at the same time, and it will just freeze your users right at that place. And if you look at I found some links from websites who say, yeah, so UWP is really bad for exhausting, can exhaust your system resources pretty fast if you have lots of traffic. And now with the introduction of the thermal netting also, you get 2 events for every event. One goes to the UWP, another is to anybody who's subscribing to netting. Like in our case, we subscribe to both of them, so we get 2 events for every one event. And UWP also has another mechanism on top of it. It generates 2 events. One is for kernel, one is for anybody who is subscribing to UWP. So we're still talking about 3 events per event. User space. So that's the issue. And so one of the solution is, like in our case, we could, when there's a problem for the user, we could rate control the event at firmware level. Yeah, we just set some value that doesn't end up so fast, and we could clearly program in BIOS level. So that was good mitigation. But if really wants to solve it, we need to really coalesce all events at the same time in user space kernel. Currently, it just blindly sends it the moment you call. So that's one option available. The other option is to duplicate user space kernel. I think this was discussed before. We really want to duplicate it, but there are lots of legacy issues. I know some Chrome Swahili are using, maybe 5, 6, 7 years back. If you change your kernel, then there will be problems. User space also changes together, it's fine. So there are some legacy issues with just duplicating it. And replace with basically thermal netting. Because thermal netting is better than UDEF because it doesn't correspond those many here. But that's not enough because there are lots of events which are there in user space kernel are not really there in the thermal netting. So we need to add new events and that's great. So what do you think? Duplicating user space kernel is the right time or? Is the user space get affected?
So I don't know, to be honest, and I don't know who's using it. So anyone using a user space governor for thermal?
The only thing that can see the only potential problem that I can see, lots of testing systems might break because of that.
That's a good one, yes. Yeah, so we'll get reports, but yeah, well, okay.
But if you have debugger replacing all those
But we can always try to remove it and see, what happens. Like often, right? Somebody or asking the list, I think, would be the first step, right? Who cares about it?
If I am not wrong, these events are handled by thermal D. And, but you are the maintainer of thermal D?
Yes, but we subscribe Netlink generally also.
So it's no longer a problem.
Yeah, it's not.
Okay.
So, but I think that the order of actions would need to be to get parity with the user space governor first, and then say, hey, we have this in the netlink mechanism, so we don't really need the user space governor, and then maybe remove it because that other thing is more efficient.
Yeah, that's fair. Yeah, maybe I will try that. Yes. Unless anybody yes, people will complain.
Yeah, well, tools will complain. Yeah, that's so. But
yeah, we need so let me go to the next one. So there are some issues with thermal network also. So, right. Even thermal network, what we see is, at least our systems, get a lot of noise. Because, at least user space governor had a control, like we have, on some system, we have 32 or 30, more than 32,000. Half of them are managed by kernel, Half of them, some we won't be interested in user space. But I cannot just change the policy, but to get the events on interested, but now you get everyone gets it. Because that's the problem, because we don't want more noise than what we already have. So, and also we have we get a multi-class group event. We have only two groups in on the sample and on the event. And we have three types of events there. Everybody gets all of them. So that's one problem. The other one more problem is if you call anytime now to update, you at least spend hundreds of cycles just to try to send message, because even if there is no user space, because when we call this generic send message, because GNF send message, it will fail at the end when there is no user space. There's no check in between that don't do this computation if something fails. So I think Netlink allows you to listen to the user space findings. So we should probably have a handler in the Netlink. Though it's no user space, don't even bother to send it. Yeah, and it's good, but it still has issues here. So I have some numbers. This is for us, notification is not just for display or debugging. It takes action. Right? So K object event to take action on one of the systems is experiment. On the max, you can see 20 microsecond later it comes in response, because it's always so overhead. Generated Netlink reduced by third of it, so now it takes 100 microseconds. But still, you have 100 microsecond delay after you say that I got an error. So you got an interrupt. After 100 microseconds, you will take some action. So this is okay most of the cases, but there are some corner cases which we have where we have to. So firmware asks us to some notification, and we don't reply in certain time, it will resend it. So good part is it resends it, because we may miss the first one. To acknowledge the first one. If it does to a character device, it only takes 16 microseconds. It is still an overhead, but I would see that character device is much faster.
Excuse me, can you repeat the test? What represents this
essentially
value?
you get an interrupt, and there's a user space handler. He reads it and he replies to firmware again.
Okay.
So that's the cycle time.
Okay.
So for thermal network, I suggest you should have corrective, we have commands, right? We you should have also a filter of zones command. It should not just send every zone. By default, because of backward compatibility, you can send out. But if someone say block these zones, then that's fine. Also policies, right? Like particularly currently policies, filter is important because if you configure the fair share, you also get one more event of CJ. Whenever the cooling device changes, state also changes. So you get like flip up, flip down, CJ update, 3 events per change.
Hey, I don't know enough about Netlink, but is this something that you can kind of filter, like you would filter out network packets?
Yeah.
Couldn't you use BPF to filter out like a firewall kind of?
Yeah, it's a similar concept. Yeah, there's a filter. I think there's a Netlink net filter exists. I think many users inside kernel.
So should we add that or?
Yeah,
Okay.
that's what my suggestion. How do you add it is a different thing.
Okay.
You add a command or something else. Also, we can check the user space. Also, if we check the user space present before we start to anything, and also we can create at least 3 multicast groups. One is for trips, another is for the cooling devices, and third is for which we care mostly is about our capacity updates. So you like for currently we have demons which are only ones interested in capacity event, but they get all. So they get backup for 3-4 times more than they should be. So all the events, whenever the capacity changes, normal event also happens. They all
So-
get triggered at the same time.
Yeah, basically it all boils down to having a way for users to specify what they want, right? Yeah. So they don't have to get everything and then filter by themselves because that doesn't scale. So, all right. Any comments to this one, Daniel?
Can we just create a filter for the events instead of creating new multicast group? Yeah, but instead of adding more multicast groups, just set a filter, say we are interested in this kind of.
But then you have a problem because if you have two subscribers.
Yes.
In your case, you have two
Yeah.
subscribers.
Yeah. Right.
Then if you have one of them set filter, you should will be gone for you.
Yeah, I don't know. I don't know if we can do that per client or not. Yeah.
Okay. Anyone? Done. All right, so we are now going to have a 15 minutes break, mostly because I need to get in touch with the.
One of the last one.
Okay, you see, you have more. Okay, good.
I think we should get this ACPI notifications also.
Good question. Yeah, I didn't. So when I was writing the ACPI driver, recently, I didn't remove those messages because I wasn't sure.
Yes, I think because I Googled it, I couldn't find anybody really subscribing to those.
Okay, so yeah, again, let's try to drop them and see if anybody screams. Okay, good idea. Thank you.
Thank you. That's my last slide. If you have more questions, yeah.
All right, so thank you. Thank you. So let me repeat the last message. So we are having a break, 15 minutes. I need to get in touch with the remote presenters. So if you present remotely in the next hour, please stay on the meeting. I will talk to you.
formula where you put the
Okay. I will try to give you a presenter right now, and please check if you are able to present.
Hello, hello.
So you should be able to change the slides now.
Yes, on which button? I'm on slide 13.
Yeah, okay,
Yeah.
good. Good. It works. Yeah, we can hear you. So great.
Good.
Thank you. And then, yes, why is, I'm not sure how to pronounce your name.
Yes.
Sorry, can you repeat?
Yes. Okay, so let's do the same thing. I will give you a presenter now. I have to take it from more than, but I will give you a presenter in a while, and you will check if you are able to change slides and so on. All right, yes, so you are a presenter now. Yeah. Okay. Great. So,
Yeah, I
okay,
can
so all
change
set.
it.
Yeah, all set. So we are starting at a quarter to the top of the hour. All right. Thank you.
I'm good. That's why you want to sit down. We can put it in the hot squeeze it, and then message me.
Okay.
I think it's there.
No, but I've done it with more advanced. But is it using the shape order to present the customer?
Yeah, you're.
Okay, then yeah, start. I would like. Hey, can you bring me a bottle? Carlos, can you bring me a bottle? Yeah. It's a cup. Huh? They don't have bottles. They're just moving out, but they try it. Bring it here. Yeah. Yeah, the DC guy, yeah. Sorry. Where is it? Yeah, I see it. What are them here? You enjoyed it? Yeah, that's right. Yeah, I remember Yeah, yeah, yeah.
it's not John Martin. It was quite a broad. Yeah, yeah, yeah. Yeah, well, not very good. Yeah. Well, about a year ago, yeah, well, we, that's also. Yeah, so I was right before that season. So moving. And then we're back to blocks.
Good afternoon, everyone. Good afternoon, everyone. I'm Salon from the Android Common team at Google, and this is my teammate David. We're here to talk about VM workloads and how they interact with the CPU frequency and scheduling. This is a continuation of my talk from LPC 2022. To give a really quick overview, workloads running inside a VM, they get terrible performance and power for mainly two reasons. One is the load tracking inside the VM is not accurate because there's no concept of the physical CPU's architecture and frequencies. On the host side, the DBFS behavior is not good because it doesn't know about the workloads running inside the vCPU. So like things migrating, IO boost, stuff like that. So how did we address it? For the architecture awareness and frequency awareness, we just updated FastVM to add the relevant DT properties, considering it's an ARM system for us. So we just added the DMIPS per megahertz property to the vCPU nodes and the operating functions. And then to address the CPU frequency awareness and node awareness, we created an MMIO CPU frequency control device. There's one register to set the frequency, another to get the frequency. So when the vCPU writes to it to set the frequency, you trap into, or let me talk about the other way. When it reads the register to get the frequency, it traps into the host side, reads the current physical CPU frequency, and sends it back. But that part's only used if you don't have a virtualized CPU performance counter, so like AMU and CPCC. And then when you write to the register to set the frequency, you tap into the host side and you set the uClamp for the vCPU thread. That's a high-level idea. And then does this work at a fundamental level? So let's look at some synthetic workloads. This is very similar to what I presented in last LPC, but with how does it look like with the fixes? So the first trace you see up there is showing how it looks like on the host. The middle trace is how it looks like without the fixes, and then the bottom trace is how does it look like on the VM with the fixes. And you have a small thread running on a little CPU, and it becomes a big thread and runs continuously. On the host side, it takes 180 milliseconds to go from fmin on little to go to fmax on big. Without the fix, it never migrated because it had no CPU frequency, CPU awareness. And then with the fixes, it takes 183 milliseconds. So it's pretty much the same as how it does in the host. And then if you kind of zoom in and look at, okay, how long does it take to go from fmin to fmax on little? Again, it took 47 milliseconds on the host. Without the fix, it took 34 milliseconds, meaning it's too aggressive because it thinks everything's running at fmax. And then with the fix, it takes 46 milliseconds. So again, really similar to the host. Into the other half of it, once you migrate into the big, how long does it take to ramp up? It takes 133 milliseconds on the host. It takes 188 milliseconds without the fix. And with the fix, it takes 135 milliseconds. So again, within error margin of the host. And new thread boost is another thing we had pointed out wasn't working last time. So if a new thread starts up to get fmax, you have a feature to kind of get it to fmax sooner. So on the host side, it took 33 milliseconds. Without the fix, it took 78, at least 78 milliseconds. And now with the fixes and the feature, it takes 32 milliseconds. So again, very similar to the host behavior. Those are all things we've fixed. One thing that is an open item is that in this case, they consider these two threads. They are taking 50% of CPU capacity and they're running on the same cluster but different CPUs. So the CPU is at fmax by 2. And when they both migrate into the same CPU, the CPU frequency is bumped up pretty quickly to fmax. It will take 12 milliseconds to bump up to fmax on host. But with the features that we implemented and with the default uClamp, when the threads migrate into the same CPU, one of them is running on the host, another is running inside the VM. And the VM, the workload running inside the VM is migrating from one vCPU to another. And the physical CPU, they end up on the same CPU. Right? So when that happens, because uClamp is treated as a max of min, if you set a uClamp min, we don't ramp up to fmax quickly at all. It's as if like it didn't know anything. It slowly ramps up on the host side. It takes 66 milliseconds to get that max. And then we kind of played with what we call as additive uclamp. And basically we apply the uclamp, actually uclamp min to the utilization of the thread, not just the run queue level. So effectively, if you two different threads set the uclamp for themselves, because you're applying it to the utilization and then you add the util, it's effectively like an additive mode of uclamp. You can kind of look at it that way. And once you do that, it's kind of blocked here. But once you do that, you'll see it ramps up in the same amount of time. So it behaves very similar to how it would behave on the host. And that's kind of like the high-level overview on how it works on a fundamental level. David did a lot of the patches and coding for patches, and he's going to do a deeper dive.
Yeah. So your MMIO mapping, right, from host to guest, what's the access control for that?
What do you mean access control?
I think your guest is directly writing to MMIO, right?
It's a virtual device, MMIO. So it's a virtual device.
Oh, virtual MMIO, not the.
It's not a real device.
No, okay.
I'm David. Let's take a closer look at some designs we did. So because we wanted to start with sort of what we can get with the best performance, we decided to use a low latency interface such as hypercall to do the guest and host communication. If we just follow that purple arrow here, you'll see that the guest CPU frequency driver makes hypercalls to either set frequency or get the current frequency. We submitted this as an RFC to get feedback from upstream, and based on that feedback, this is our current V3 solution where we use MMIO and uclamp instead of hypercalls. So if you follow the same purple arrow in that diagram here, instead of making hypercalls, it's reading and writing in MIO regions, which then gets handled in the host. The host has to now defer up to user space. The user space has to make additional syscalls back to the kernel. So as you can see, these additional context switches cost is pretty significant performance hits, as we'll see in benchmarks later. So this is where BPF actually could be a potential solution for us, where again, guest sees the same interface in the MIO, but now in the host, instead of having to go back up to user space and paying additional penalty for latency, it can be optionally handled in the BPF program where it makes BPF kernel help function calls and increasing our performance as a result. So let's take a closer look at some of our benchmark results. This is running PCMark inside an Android VM on a Chromebook. We chose something like PCMark because unlike Geekbench, where it just runs everything at max, we wanted something that emulates real-world use cases such as web browsing, video editing, and some other categories, as you can see there. The blue bar on the left is baseline, so you'll see that all the prototypes are performing better, with V1 being the most performant, and then V3 having a performance penalty, but then adding additional improvements such as additive uclamp and eBPF helps us get to the performance point where we were at. On the left, you'll see the score, and on the right is efficiency, which is perf over milliamp hours. So similar story, running Roblox inside Android on Chromebook. Again, V1 being the most performant, along with V3, it's the red and purple bars. Next up, we have, this is running storage use space inside an Android VM, inside on a Pixel. Similar story here, most performant being the red and purple bars. And finally, we have some CPU ML-based workloads. And in this case, the lower latency, the better. You see that the red and the purple are the most performant.
And so coming to switching over to discussions, really only two topics we thought we'd ask. Feel free to comment on the existing ones we talked about. But first is, can you do additive uclamp? And the second one is eBPF. Maybe eBPF might not be the best thing to talk about here, but for additive uclamp, you just kind of like scribbled up some patch today, literally, just to give the idea of what we're talking about. No, this is not necessarily the correct patch. But the idea is to basically take the uclamp. If you set a flag to apply to the task util, then you set the uclamp for the util and util-less functions. You just clamp it to these values.
Got a question online?
And that's pretty much the last slide. So we have 5 minutes for questions. Dietmar, maybe?
Yeah, but maybe your RC that you had like util guest, right? Is util guest exactly your additive you clamp now?
Yeah, util guest was something you can hack up quickly, and additive you clamp is more something you can expose to syscalls, user space. It's not useful just for the other things. But the idea is the same.
Okay, and you're saying that like if you would have some aggregation on uclamp, then your system would behave better because your vCPU thread could essentially ask for the bandwidth it wants, right? Like you have issues with
kind of breaks down.
aggregation.
Can everybody else in the call mute themselves? There's a lot of noise is coming. But Dietmar, if I understood you correctly, you're asking, do you see clear benefit with the additive uclamp? Is that right?
No, I'm just saying we have in 30 minutes we have a talk about some aggregation on uclamp versus max aggregation, and I think your use case is essentially falling into this area as well.
Yes. Yeah. Any other questions on the call?
Yeah, there's another question.
Please, who should go next?
Hi, this is Chris. Can you hear me? Yeah, just one clarifying question. Did you propagate the utilization from the guest to the host, or did you propagate the specific frequency that was requested?
So we take the frequency request coming on the guest side as an indication of the utilization.
Okay, thank you.
For example, if you change the governor to performance, we still wanted it to work. So that's kind of why we did it that way.
Okay, thanks.
This question in the room.
Yeah, so for the additive part, I don't know, like it's a big part of the confusion with uclamp. It should be a performance hint really, and not like the way with the adding it, like it hints that you require some bandwidth exactly. So the devil might be in the details, but something that I have concern about is that uclamp should not be added at all, or at least not treated as a bandwidth, which seems what you are trying to do over here. One part that I didn't understand is that you said the max aggregation is a problem. And to be honest, it is generally a problem. If we remove max aggregation altogether, will this fix your problem, or will it still be there?
No. Max aggregation does not meet our needs, right? So here
the max
aggregation and this part right here. When thread migrates from one VCP to another, on the host side there's no awareness, but we do set the uclamp min to say like 512, right? But you take the uclamp min and then you apply it to the existing utilization there. But that vCPU thread had a utilization of 0 because it never ran sufficiently before, right? So you're saying set a uclamp min to an existing run queue that has 50% already. That has no impact. It's useless. You have to add it because workload is migrating from one CPU to another CPU.
Yeah, I see your use case, but I don't know if that will be treated like as an acceptable exception or not, but I think we can discuss on the list, but yeah.
2 more minutes. Any other questions? I know Amy,
yeah, I have a
thoughts on.
I have a question. If you can hear me, sorry.
We can hear you.
Actually, I'm Hongya. I just replied on the email thread. This is not a technical question. Do you have like a guide or walkthrough on how to replicate your setup? Because I'm also doing the sum aggregation, uclamp sum aggregation series, and it seems like what you are doing with util guess is exactly as the thing I'm trying to do with uclamp, with the new uclamp. So if I can replicate a setup, I can try and see if the benchmark scores can be as good as the util guess you just added. So yeah, can you point me to somewhere I can just set up something like that? Like yours?
The patches you sent out should work if you're using a DT-based system or a system where you expose the CPU frequency to the host. So if you have ACPI where the actual frequencies are exposed to the host and it doesn't use schedule on the host side, then these patches wouldn't work. Otherwise, you should be just able to apply these patches. Just go look at V3. That's all the details. For uclamp additive, we don't have it, but we'll happily send the patch soon.
Okay. So what's the device that is used to do the benchmarking in your series?
This is either a Pixel device, Pixel 6, or it's a Chromebook, one of those two.
Okay. Yeah, I do have a Pixel 6. Yeah.
So one is like running Android instead of Chrome. Okay. Okay, out of time. Thank you, guys.
Okay, thank you.
Okay, so the next presenter will be Luis from AMD, and he's a remote presenter, so I'm now going to make him a presenter. And
am I audible?
okay, so these are your slides, right?
Yes.
All right, so now I am going to make you a presenter. Okay, you should be all set.
Yeah, thank you.
You have 15 minutes for your topic, including discussion.
Yeah, thank you. So, hi everybody. This is Wes Carney, and I work in scheduler and power management team at AMD with Gautam. And in this presentation, I'll be talking about VM CPU Freak for x86 systems, scaling the guest frequency for performance and power saving. So, little bit of background, how Linux kernel scales the core frequency. It basically uses this formula, f next equal to 1.25 into utilization into f max by capacity. So here for x86 systems, f max and capacity are static, and only variable part is utilization. And how Linux kernel um, decides the utilization is depicted here. I'll not go deep about this utilization calculation, but ultimately this utilization is calculated and aggregated in the run queues and ultimately fed to scheduler, and scheduler calculates this frequency and give it to frequency driver. So we did one experiment where I took a workload and ran it in a virtualization case and in a bare metal case. And in virtualization case, I have measured the utilization in the guest and host simultaneously, and bare metal case I have measured separately. So if we see the 90th percentile, the workload I ran is a simple loop which has two phases. One is busy and one is idle. So when the idle phase is 100%, it means 100 microsecond it waits and wakes up and again goes back to sleep. So this workload, if I run in the virtualization case, then a 90th percentile of utilization becomes 41. If I measure it in the host, it becomes 42, and only in bare metal case, it will be 17. And if I vary this busy percentage a little bit more, 10% busy, then this becomes 133, 104, and 108. For 50% busy idle, it becomes 497, 523, and 495. So it's in the same ballpark, but here actually the guest is performing halt, and which causes a idle, which causes a VM exit uh, when guest is idle. So, but we saw a problem when guest does not idle, so does not exit when idle. So some cloud providers do not want guest to perform VM exit when guest is idle to achieve lower latency. And what they see like they use idle poll or idle MWait to do that, and they see higher power consumption for idle poll. And there actually we did some measurement and saw that when this graph depicts the same workload characteristics, and if I vary the busy percentage from 0 to 100% and plot the 90th percentile in the y-axis, So when guest uses halt exit, and this blue line is the VM's view, orange line is the host view, and green line is the bare metals view. So you can see like host view tries to tries to match the bare metals and VM's view, but it's not exactly accurate. But for halt case, it's acceptable. But for pole and MOID case, host always see 100% utilization. So this is not correct for idle pole and idle MOID. So um, uh, we evaluated VMCPU freak patches from Google, and there are mainly two versions of this, V2 and V3. So V2 is based on ARM Big Little architecture and focuses on pinned VM and uses hypercall. Google's main uh, problem was their guest workload task placement. But for our case, x86 server case, the problem was a bit different because we have a same capacity cores and we don't have a task placement problem. But we have a problem when guest doesn't exit on idle. So that's what we wanted to solve. Uh, we picked up a V2 and how this works. I'll not go details on this because Saravana has covered already in the previous LPC talk how this works. So we ported those patches for x86. And results, actually I have tried T-bench, D-bench and current bench workload, and the results, if you see the T-bench results, like first case is the halt case, and second case is the idle pole case, and third case is the idle MOID case. So, and this black line is the no driver case, and red one is the VMCP quick driver case when case is running VMCP quick driver. So you see only red lines because it's overlapped, and we don't see any changes in the performance. There is a little bit variation in the power, but it's very minimal. Same for D-bench, there's very minimal improvement. And you can see that if I use idle pole inside guest, the power consumption becomes 10x. And current bench also, I don't see any improvements either. These all results are of 8 vCPUs results. If I vary the vCPUs like 16 vCPUs, I see some power improvements in idle pole case, but it's not sustained. If I run many number of times, I see performance power again will shoot up. So for D-bench also same case. So ultimately, if I plot this utilization graph for this case also with VMCP freak also, we see the guest pole and MOID are still showing 100% utilization. And in the whole halt case, I'm actually seeing a higher utilization compared to not normal case, because if you see the patches, VMCP patches, it gives an additional boost to the guest thread. So that's why this is happening. So in the summary, yeah, so we don't see any performance improvement and performance and power improvement. And that is because current VMCP patches actually only consider the lower bound of the utilization, that does not consider the upper bound. So we tried adding the upper bound using uclamp min and max also, but we don't see any improvement there also. And yeah, so this is the current status of this. Any comments, any questions?
Yeah, it looks like we have a question.
Hey, Saravana here. I think went through slides. One of the things I wanted to know was, are these all CPUs in the same cluster or are they independently scalable? Because they're all part of the same cluster, the whole thing, VMCP freak stuff isn't very useful. Because if you're running in one CPU versus another, it determines the frequency the same way. So how independently scalable are the physical CPUs?
On x86, we can request frequency change independently, Saravanan. So these CPUs, I mean, at a core level, we can request a different frequency. So.
Okay. And then the other one is, when you implemented this, how many frequency points did you make available to the VM? If it's just like min and max, then again, you'll see it wouldn't be really good. You need to have all the intermediate frequencies. So is that what you did?
Yeah, so we use the ACPI CPU freak, and on servers, we have three P states, min, max, and an intermediate one. So all these three were sent. But the larger concern is, Saravanan, when the guest utilization is communicated to the host, in the code, we saw that we were taking a maximum of the guest and the host's utilization, the effective utilization during the computation, right? So as a result, since we are trying to optimize for the idle case, that was really not taking effect because the host utilization will always be higher. And perhaps we have to explore the things that you did in V3 to see if we can use the ideas from uclamp to kind of clamp it down. And
yeah, so what I call uclamp additive is really more like clamping the actual utilization of the task. We can click out as task util clamping. In that case, if you also set the max, it would achieve what you need in your case. Yeah, so I think it's more about having more intermediate frequencies. Because one of the comments was it didn't have any power savings. I think that's because you only have 3 frequency points you're making visible. Because if you make more of them visible, then you have finer granularity on what utilization of the vCPU that you pass over. Oh, and actually one last question. Are you using schedule governor? Because I know like in x86 missions, it's not the case.
Yeah, we are using
sorry, Intel
Schedule.
Okay. Thanks.
And also regarding that p-state comment, actually we have used AMD p-state also, but there also we see like performance dropped. So yeah, we have to do more experiment with AMD p-state.
Hi, this is Joel. So one of the things I was wondering was, from the host perspective, if you have idle polling in the guest, then the vCPU thread is really busy. And I was wondering, yeah, you know, you're not really busy inside the guest because you're idle polling, but it's kind of weird for the host because from the host perspective, that's a busy thread, right? And how does what you wanted to affect other threads on the host? You know, that's what I was thinking. Maybe I don't fully understand what you're doing, but that was kind of my question.
So Joel, the intention here is if we are able to communicate the frequency requirement from inside the guest to the host, say we ask for a lower frequency, that should translate, or we share the utilization rather to the host. We should be able to take that into account the next time the schedule computes the frequency, right? So it knows that there is a guest thread that is running which is not doing anything useful, and take that into account while determining the next frequency, and thereby ask for a lower frequency. So that was what the intention was, because these vCPUs are pinned.
So that, Vincent speaking. So the utilization on the host side is how much your vCPU is using on the host side. So it's normal that is increasing if you're doing some pooling, because from a host point of view, you're not idle, you are running. You see the point? So you can't really screw up the host utilization just because it doesn't reflect correctly what's going on in the vCPU. You must find another solution, because this is then used in the CPU side to know how much of the compute capacity is used, how we can balance everything. So You can't just change that and expect to reflect that. You must find another way. I don't know which one, to be honest, but this utilization on host should reflect what is used on the host point of view.
Just one quick comment. I was kind of talking about this to Asan earlier. The way I see it is, for min, we are taking the input from VM, CPU Freak. Take it for max. So basically, long story short, host has no idea what the utilization is. Instead of trying to guess and do stuff on the host side, just listen to what the vCPU is telling you. If you're setting min, set the max. So that's one. And then please work with me. Like, feel free to email me to figure out your patches. If you need more help with that, happy to help. I think we're running out of time, right? Yeah, thanks.
Sure. Thanks for the feedback, Vincent.
So the next presenter will be Chris from Intel. And
Yeah, definitely. I have a talk at 5.
Yeah, I'm here.
Yeah. Okay, thanks.
Chris. So I'm now going to give you the presenter. Right. So Chris, you should be a presenter now.
Hey, thank you.
And you all set?
Yeah.
Okay, cool.
Yeah, thanks.
The floor is yours. You have 15 minutes for this topic.
Okay, thank you. Hi, folks. My name is Chris McNamara. I work with Intel. I also prepared this presentation with Srinivas, who is in the room there. So you can ask him all the hard questions after this is over. I'm based in Ireland here, so I'm joining remotely, as you can see. Okay, so what I just wanted to talk about quickly, I have about 3 slides, is the opportunity that's there from a telco point of view. I'm going to talk a little bit about the characteristics of the telco workloads, some of the challenges that we have, and some of the opportunities that we have to hopefully solve some of the problems we see. But just to introduce this, ultimately, you're looking at a 24-hour period. If you think of a server that's processing traffic from a phone, a cellular phone, it's running over a series of servers that you can see over a 24-hour period. The load will vary based on what's happening off-peak at nighttime and during the day. But ultimately, we see a mix of adoption of power management technology. So for example, during times of peak, we can use technologies like Turbo Boost, and during times of off-peak, we have opportunities to use C-states, P-states, etc. And I think the most important point here is that from a telco space is that it's a fixed dimensioning. So what you get is you get a set of servers locked in, and they're always on. They don't tend to scale in and scale out compute resources. So that brings opportunities for power management. So what I'm showing here is just a graphic that shows the host and the guest on the right-hand side. What you can see here on the right, if you can see my mouse, is a user space application. Some of these telco applications tend to be polling. They tend to sit there polling, they tend to be pinned, isolated, and they tend to live for very long periods of time. So the nature of those applications prevents and negates the impact of the power governors that are in the OS. So what you're seeing down here on the right-hand side is user space application. It's outputting some performance indicators and some utilization to a user space power governor. So one of the solutions that has been employed in this piece here I'm going to talk about, but you can see an opportunity where the user space power governor is interfacing to the sysfs for scaling min, scaling max. It's taking utilization outputs from the user space application because the OS sees this as 100% busy. Okay, so power governors are pretty much negated. We also have challenges around root access. Applications in many of these environments don't have privileged access, so having user space power governor that's a separate entity allows us to build that out. Some of the challenges have been implementing a power management scheme within an application is, not palatable for many customers that are adopting this. So having the user space governor works quite well from monitoring resource, measuring, and taking that power management action, be it maybe a P-state scaling action. From a metrics point of view, like I mentioned, the OS doesn't have a way to suck in user space utilization in a custom way. Well, maybe until I saw the previous presentation by Savannah and David. But one of the key challenges is the diversity between somebody who writes a scheme that works on the host that's not available in the VM. Okay, so availability of power controls in the guest for these environments is a blocker for adoption. Okay, I hope that's clear, and I just put a graphic up here that showed some simplistic view that you don't have control from a user space power governor that you implemented on a host isn't available to you in the guest environment. Okay. Let me click on. Yeah, so if you were to solve this, or the components that are in a solution today, what I'm going to focus on the virtual machine in this case is that if you were to build this out, we would need as we launch the VM, we would need to attach a transport to the VM. So we would have a custom API here that allows for the user space governor to proxy P-state requests from the guest to a host. Okay, so that would involve implementation of a custom API. Virteo serial, I would argue, wasn't really intended to be used as a transport for P-state requests, but it is a pretty low latency interface in terms of, you're talking milliseconds here. So you're essentially building plumbing for the guest to the host to proxy P-state requests, right? You would also need a user space governor backend that would listen at the other end of that Virteo serial transport and suck in the P-state requests so that they could be applied through CPU frequency or Intel P-state. Okay, so where we can see in this graphic is that we end up in a situation where we have an application that can benefit from power saving. Its utilization is preventing some of the traditional or typical techniques that we have from being able to make any power saving decisions. We have customer base that isn't necessarily looking to implement or change their applications. So introducing this user space power governor is received pretty well. But I would argue that this is a non-standard way of bringing P-state requests from a guest OS down through to the host OS. Okay, so what I would say for this is that we end up building a large number of interfaces and transports and software to be able to support this type of architecture. And as you look at this, you would see that,
I have a question.
Oh, please, yeah.
Yeah, so you're saying that you're using the Virteo serial interface as a way to communicate. Have you looked at the Virteo SCMI interface, which the SCMI is System Control Management Interface? That's a Virteo device which provides you access to some frequency scaling, performance domain, and power state. Maybe that would be a better way for you, for the guest, to provide some performance hint to your backend.
Yeah, I wasn't aware of that. What I did look at was Virteo serial, Virteo user, and Virteo VSOC, and the latency. Yeah, they were the obvious ones, and even IVSH mem as from a shared memory segment. But there were different challenges with many of those, primarily around the latency. Virteo serial did give us the most consistent latency, sub 3 milliseconds. There were some outliers. I think I have them written here. What did I put? Yeah, so we had some outliers, but I think you mentioned SCMI. So I'll definitely check it out. Yeah.
SCMI is also implemented on top of Virteo, right?
Yes.
So I think you're going to have similar.
My point is mainly because instead of using Virteo serial and put your own string to set some performance, just use Virteo CMI. Everything is already defined, so the guest can say, I want this kind of performance. That's my point. Saying if I mean the point of is Virteo the best way? That's another discussion.
Okay.
Yeah, that's a good suggestion. Thanks. Yeah, go ahead.
Another observation. So you mentioned the latency for setting communications on the order of milliseconds. So when I was doing testing, I think with hypercalls and BPF solutions, we're getting in the orders of tens of microseconds, and it had a pretty significant impact on performance for us. So it's something that we observed.
Yeah, thanks for that. That was one of the things I wasn't sure that, but I think that's a good suggestion. If we can get to microseconds, that's even better again. Yeah.
One of the usual question, because it's always confusing to me, are you using schedutle? I don't know how schedutle and x86 work because you use EPP.
Yeah.
So there's no schedutle. Okay.
No, the decision.
No, on the host side. User space there too. Okay. Quantity is done. Okay.
Yeah, it's not like you clamping or other thing, because here the application itself is smart enough to tell utilization, because it's all constantly polling. It's a telco workload. It's very
so you're just trying to get the pipe the value.
Yeah,
through
it's like
the
every
host side.
200 microsecond of this.
Can't you just set it on the host side and call it a day if you're not really trying to pipe anything through?
So if my understanding of this is correct, it is about the application anticipating its needs, right? So it will say, I will now need this much of a performance going forward,
Sure.
and like pass it to a host through all of the
Okay.
All of this, yeah.
Yeah, so it's not expected to change very often, then I guess whatever protocol.
So there is just the application is the driver here.
Okay.
All right, so 1 minute left. Any more comments?
Oh. Yeah, just finally, thanks for your time. Thanks for the feedback. Appreciate it. So thank you. And you can ask Srinivas, or if you want to contact me afterwards, if any other suggestions, I'd love to hear them. So thanks again.
Great, thank you. Okay, and next presenter is going to be Morten from ARM, who will also present remotely. But I need to switch over to his slides. Come on. Yeah, I am. No. Yeah. Right. So the slides are up, and now I'm giving the presenter to you, Morten.
Yes, thank you.
All right, all set. Again, 15
Good.
minutes.
Thank you very much. Thank you. Yeah, hello, I'm Morten. I work for ARM. I work alongside Dietmar and Honyan, who's joined me here on this presentation. So we're going to talk a little bit about uClamp, and I think Saravana did an excellent job earlier in sort of starting the party. So we'll skip quickly over the motivation slide because we all know what uClamp is and why it's there. It's been in mainline for quite a while, and it has a few gaps, I think, in the current implementation that others have experienced as well. So we've had a good look at what are the problems and what can we do with it, and try to fix it. So the main issues we really see with UClamp is two things. One is the aggregation of the per task UClamp settings when you sort of combine them on a run queue. Do we sum them up, or do we use the max aggregation mechanism that we currently have upstream? And the other thing is the complexity of the implementation. At the moment, the implementation doesn't really track the clamp value from the source all the way to where they're consumed. And that means that we need to do quite a lot of computation every time we need to use a clamp utilization value. And perhaps it's time we revisit some of the implementation choices we did. I tried to summarize how UClamp works in upstream as it is today. As Kai's pointed out during Saravana's talk, UClamp is currently considered a performance hint that's describing the desired throughput rate rather than the actual desired throughput, as in a task can ask to run at a specific frequency, but the request doesn't actually imply any throughput reservation or any throughput guarantee. So that means that if you have a run queue with two tasks on it, and you have, for example, UClamp min set, you just take the max of the min request, and that will be the min clamp applied to the utilization of the combined run queue. So for this example, the resulting frequency is the same if we had just one of the tasks on the run queue as if we have two. The kind of throughput or the compute capacity in UClamp is shared with all other tasks that's on the run queue, and that's particularly unfortunate for UClamp Max, because it kind of in the existing implementation allows UClamp to place as many tasks on the same CPU. It doesn't really have a way of spilling over to the next CPU. So in this example, I've taken 5 always running tasks, and you can basically, if they all set a UClamp max of 512, which would be sort of 50% of peak frequency, it would be totally valid to put them all on the same CPU and keep the CPU at 50% of its peak frequency. So while all the tasks are asking to run maximum 50% of max throughput, they're actually only getting 1/10 of the maximum throughput. And that's allowed in the current implementation. And I think that makes UClamp, especially max clamping, particularly hard to use.
So yeah, Dietmar, I have a question. Yeah, you can hear me?
Yes.
Vincent speaking. Yeah. So for your second use case, I would say, why are you packing all the tasks on the same CPU? That's the point. I mean, the point is that the UClamp there is just to say, for this task, I want this, at most, I want this amount of bandwidth. And then you are packing all the tasks on the same CPU, but why, I would say?
Well, there's no mechanism to force the task away.
Sorry?
There is no mechanism to force the tasks away right now. There won't be balanced to other CPUs.
No, right
I can
now,
actually
but
show that as.
So just because the NLP-aware scheduling is want to pack everything as much as possible.
No,
But
this is okay. I think you're taking the example too literally, right? It's just an example of, hey, if 5 tasks end up on the same CPU, and they all set this UClamp, you're affecting others in this way. I don't think you're supposed to see it as like as a literal like this is the only thing that's going to happen, right?
No,
or
it's
maybe somebody's like pinning their threads.
Yeah.
Whatever, right? But you still need to operate correctly in that situation. I think that's what.
But the point is, it's there is that, I mean, you said I don't want more than 500. That's the point, and that's it. So that's why for me it's
yes,
not. I mean, you can't you put yourself in a situation where everything is wrong. Change your configuration.
You have an example with min. I think we can move on with that one.
Yeah, I think using uclamp min is a better way to convince other people. Like if I say uclamp min of 100, if there is like 100 tasks on the CPU and I have a uclamp min and this min moves me to that CPU, I'm the 101st. I'm living with all the 100 CPUs, and I'm not getting I'm not getting the CPU bandwidth I want, even though I specify uclamp min. Like the max aggregation cannot solve the problem that you can have like 100 CPU, 100 stuff on the same CPU. Yeah, you satisfy the uclamp min request, but I'm not really getting any compute power. So yeah, maybe uclamp min is a better example.
Yeah, but that's the same for that. I mean, if you're packing everything on the same, you will have the share that you have requested. I mean, you're trying to mix a share, something that is about how many cycles I would like from the CPU and how fast I would like to run on this CPU.
No, it's that's saying this is what I need.
We want to argue we want to argue that we want to get away from the max aggregation towards some aggregation and just highlight the advantages we will get. Because one thing is clear with the latest patches in fine energy efficient CPU, for instance, we letting tasks into performance domains which are not able to have a proper or a sane energy model calculation because of overutilization. So, but anyway, summing this up, we want to get rid of max aggregation and go to some aggregation and explain the advantages here.
Yeah, maybe we can let you guys continue the slides. And the way I presented it, you can pick and choose which one you want to use. So.
Cool. Let me go on. We already spent 7 minutes. So I tried to summarize here some of the issues we have with the max aggregation implementation. So the current implementation, we have per task uclamp settings, but they're all applied on the run queue utilization. And it has one big advantage, and then that is we don't need to introduce additional PELT-derived signals and propagate them all the way up and down the task group hierarchy and all that. But there is also a long list of disadvantages, I think, that are hard to work around. With max clamp tasks, the utilization doesn't really represent the true compute demand at all anymore. So if the task is running alone and you have an effective max clamp in place, because of the properties of PELT, the utilization will just go to 1024. So we can't really say anything about that task's true utilization. And when that gets added up with the other tasks, then you suddenly cannot really distinguish what's going on in the system. And for co-scheduled tasks, they sort of eat each other's utilization, so it will underestimate the true compute demand of those tasks. The difficulty to distinguish between utilization coming from clamp tasks where the PELT behavior just keeps the utilization increasing and true unrestricted compute demand is already there. I mean, there is a patch on the list from Kai's trying to address that issue. And we have the other problem that if you have a clamp task and a non-clamp task on the same run queue, then whenever the unclamped task runs, because you have accumulated so much PELT utilization while the clamp task was running, because it just saturates the PELT signal, you see frequency spikes every time the effective max clamp is kind of lifted. The other issue is in the implementation of max aggregation, you kind of need to keep track of who's the max clamp setting amongst all the tasks on the run queue, and tracking that is kind of tricky. So in the current implementation, we have this bucket mechanism, but that kind of erodes the accuracy of the clamp settings, because at the moment, I think by default we only have 4 buckets. And then there is the whole problem that it's really difficult to reason about what will be the throughput my task can expect if I use max clamping, because you are just asking for a frequency. There is no mechanism that kind of says when should I start spilling over to the other CPUs, because what is the true utilization of that task? So looking at those issues, I think it really boils down to 2 things with the current implementation. One is that uclamp is not applied at the source, So we kind of add unclamped utilization up and then try to apply those per task clamps to the run queue utilization at the end, and we kind of lose information that way. So it's difficult to do the right scheduling decisions. And then max aggregation doesn't really provide a clear policy for how do we balance clamp tasks. I mean, how much do we need to spread them? If you have 2 tasks or many tasks with different clamp settings, how much weight should they really carry when you do load balancing? So I think there are 2 possible solutions. Either we dig the hole deeper with max aggregation. I think it's already a fairly complex implementation, and it will only get worse if we try to fix the current gaps. Or we try something new and see how bad is some aggregation, and maybe it is actually worth creating another Pelt-derived signal if the whole implementation becomes a lot simpler. So who's actually using uclamp at the moment? We were not quite sure. Given the gaps that we have in the mainline implementation, it can't be a huge user base we have. But we know Android is using it. But at least on Pixel 8, they don't really use the full upstream solution. They use it kind of on task level, but then they have something built on top using Android vendor hooks that means that it actually ends up being some aggregation on task group level. So it seems that most users, yeah?
Yeah, like just the statement about the Pixel with the group throttling. There is a bit of misunderstanding over here, because this is like the things you're talking about in the slide over here. They've been added for issues with CPU shares usage and starvations problem. Well, I think in the past there has been a talk, so I can understand why it might be related to uclamp max. But actually, what I've done is like that first solution you're talking about, the filter, that should be there. So we should be having a filter mechanism to handle the issues. But I do agree that the filtering might not be upstream friendly. I do think there is a third solution that's not in your slide, but I don't think we have a lot of time, so I'll let you go on. But I just needed to clear up that this throttling stuff, it's not really related to uclamp max directly.
Okay, maybe it's not this one, but Pixel does do addition of uclamp, right? It has implemented some. Maybe it's not the specific configurations. Has it not? I thought Pixel does addition of uclamp. Maybe it's not the exact configuration, but you guys do
Additional
it.
uclamp? No.
Like adding the uclamp from tasks, no?
Yeah, it's been done for a different reason, but like I would say that like it's to handle CPU shares related issues.
Okay,
so these ones I did like verify many times because that has been crept up, but like no.
Okay.
I think we were aware of this issue that those 2 config options, they might target the initial problem of CPU shares not giving what you wanted. But I think in our discussion, we think more and more that the sum aggregation of uclamp max actually can provide you with this functionality as well. So we could have a mainline implementation which you guys are using also for your initial CPU shares issue. But we can take this offline. It's a too long discussion.
Yeah, my point here is really, can we not agree on a usable upstream implementation of uclamp? It seems that a lot of potential users are seeing things quite or somewhat different from what we have upstream. And that was kind of where we were as well. So Honyan has been working hard on an RFC patch set that's actually on the list that takes a stab at some aggregation. So there are no changes to the user space API. Fundamental goals remain the same. We add a new Pelt-derived signal and we propagate that all the way to the run queue. That is making things simpler, but there is also some maintenance overhead in there. So I think that's something that needs to be discussed. It makes the code a lot simpler. We can reduce the lines of code related to uclamp by about 50%. And the preliminary results we have look fairly okay. It's not the final solution. It is an RFC, but I think it's worth considering if we should try to clean things up here. So we're essentially out of time. I have more slides that you can look through offline if you want, with a few examples of how it performs.
Just a quick question. I haven't seen the patch that you're pointing at, But wouldn't you have to clamp with the way that I showed in my patch, like in my slides, like a demo patch or whatever, that where you have to clamp the actual util average? Otherwise, your U clamp max will never get applied, right? Because you're going to end up picking the highest of the.
Yeah. So the way it works is that at the task level, we actually apply the clamps directly to the util average. So we have a new util average U clamp that is propagated all the way from the task to the root run queue. And in
Okay,
this
so pretty much kind of
example,
what I showed in the.
yeah,
Okay.
I think it's the same thing essentially.
I'm all for your proposal.
We are going into the break now. So I would suggest continuing the discussion on the list or in above maybe or something like that. If somebody wants to set it up, because we have no more time.
Okay.
So
Thank you very much. Thanks for listening.
Thank you for bringing this up. And we are now having a 15 minutes break.
Please.
Hi, Rafael, can you hear me? Hello, this is Ray. Hello.
Sleeping on the bus. Call whatever you want, the name, right? Call B class or balance class. The point is, that's the case where I am saying more balance is not how do I give you that information? It's not given 100% value. Balance is like, no, vacancy is. Okay, I don't know how since you can't say I'm not saying to break the way and do this. What do we want to call it? The point is, in terms of saying I'm going to have is not case. So then give us a way to get that. The one thing I was showing is like, I was just showing you how consider the cycle number of cycles. By filling up the names. My utilization is slow, but I want performance. So those is why we get otherwise I mean I will run slowly. Then I cycle back. Is that I'm using all the cycles I can. I don't care if it's use all the cycles I can get. For example, if you say I want to run 1:10:24, I will allocate all the CPU for you because you say I want all the other cycles. Right. And that doesn't work because all the is actually the VM, that's what I'm asking. You need a band and allocate this one. So if you want to call something else, but I'm saying I need the same way I'm going to achieve that by saying taking more and more things instead of large stuff around because we've seen like most of I'm telling you all flags this breaking back to the using set the flag I spent too many within a fiction. What other because that I think I see, okay, for now it's calling the at least we are for now it's a performance. I want that. At least with the current design is so like adding it will be better. I'm not saying change you have exactly, that's it. And then you so I don't know. I've been trying to. You want to say this separate? Okay, no. I think it makes sense. That's all we will say. That's another thing. I don't know. I'm trying to argue for that. We instead of continuing to add stuff to might have like special instruction. Yeah. Just not continue to add a new one. Just that's why I'm adding this class. It changes something you have to make things. I don't want to be honest. I think the English people are in this school is confused. I mean, what the hell is which we can showcase it. I think it's just like super exposed, like making things a bit more complex. We have so many. Okay. Yeah.
I have no clue where the slides are. So I have to wait. No, Raphael's been controlling it, right? I just see a website.
Yes, but you have a class button.
Oh, okay.
And then I think
Will he do it for me? I'll just wait. I'll eat 1 minute. Are they somewhere on here? He said he would download them, so are they somewhere on this machine?
Do
you know where it is? Do you know where it is?
Mm-hmm.
I just see a website.
That's the BBB thing.
Yeah,
Which one is it?
But yeah, no.
It's just this one? Yes, boom.
Oh, yeah. What happens next? Anything? All right, great. Okay, I got 15, well, I have 14 minutes now to talk about a problem that's existed for 10 years, maybe longer than that. And so let's just do it. What I'm talking about today is basically this function. So in the clock framework right now, we have this function called clock disable unused. And it basically does this pseudocode, which is for every clock in the system, if it's enabled in hardware and no one's enabled it in software, then just turn it off. And we do this at late in call sync. And we do it at late in call sync because we want to make sure it runs after all the deferred probing happens. But I found out like 2 weeks ago that that's not even true. And it runs in parallel to deferred probe and also to async probe happening. So it's like basically completely broken and does not work in any way. And I usually get emails from people like every year or 2 years like, hey, I want to fix this. I'm like, great, please do. Please fix this for me because it doesn't work, right? And we just leave this code in the kernel and it's still there. And it's just like basically disable stuff all the time, which is really fun and causes lots of problems. Can I go like with the air?
Yeah.
Okay. So the other problem that we have in the clock framework that basically no one really talks about, unless this topic comes up, is that we don't really know if a clock is enabled when it's registered. We just completely ignore it. So the clock framework tries to cache as much stuff as it possibly can so that it can make things faster, which I don't know if it really is faster. But anyway, we don't really know if it's enabled when it's registered. And we don't even know if it's enabled when someone calls clock enable on it. And so we may actually go write the hardware again to enable it. So there's actually code out there, like for example, like pillow code. Pillow is already running, right? And there's a bunch of sequences that people go through. And so half the time, and if you look at a pillow clock op for enable, it says, is it enabled? Oh, let me just bail out of here. So like the framework is like just calling the clock ops for no reason. And that's another issue that no one really cares to solve or has solved so far. So right now when you register, we don't know at all that it's enabled. And we don't really care until late init runs and we actually see, oh, is it enabled in hardware? And if it is, then we disable it. The other problem I wanted to say here with this diagram of the ABC is that if these clocks are shared across different clock controller devices, so you have a struct device for B, for example, and you have a struct device for A and C, and the A and C clocks exist in one device, and all these clocks are on, and the driver for B doesn't probe, doesn't register the clock, and then late init runs. A is going to be turned off, C is going to be turned off, and B is going to die, even though it's technically on, which is bad. Also, again, right? So all this stuff is bad, right? And so what are the use cases? Well, the use cases we have are people want to keep clocks on from the bootloader because they want to maintain their boot splash screen, for example, right? And so they don't want late init to really run and disable their unused clocks, especially if their driver is a module and it hasn't even loaded yet. And so they don't want their clock to be turned off to kill their boot splash screen. The other thing is that we want to save power because people want to turn off clocks that bootloaders leave on because no one's using them. It's just burning power forever if we don't turn them off. And the other thing we want to do is like, oh, I'm on a certain kernel configuration where I don't enable some driver somewhere, right? And so I want to save power again because my kernel configuration doesn't require this clock at all. How do I know, right? So that's the topic. And I did it in 2 minutes, or 3 minutes. So what are the proposed solutions? So I'm going to go through the proposed solutions. There's like 3 or 4, maybe 5 of them, but I only have 3 here because I put them in the proposal. So the first solution proposal was from Salon, and that was actually the second one. Anyway, it's basically, let's use sync state, right? So what does sync state do? It basically just calls this driver hook when this device's consumers have all probed and gotten their clocks. That's what you can imagine. So Salon basically said, let's enable all the clocks. Let's hold that enable state when we register a clock. So if it's enabled in hardware, keep it enabled the entire time until someone calls sync state on that device driver for the clock that the clock controller is for. And then if it's registered, so then during late init, we keep the late init code. So all the clock disabling unused code still exists. We basically say, does it have a device registered for it with that? Do we register a clock with a device? If so, completely skip that clock during disabling of unused clocks. We're going to rely on sync state to run it, right? I can't even read because there's like this thing on top.
Yeah, I can. Okay. Yeah.
And so then when the sync state logic runs, right, we're basically going to call this generic clock sync state function, and it's going to just go over the entire tree, the clock tree, and then if that device matches that the sync state, like the clock sync state function takes a struct device argument, if that device matches what the clock was registered with, then we'll disable it if it's unused. Right, so we basically just push the late init call out for certain devices if they've set the clock up, or not, if they set the device driver function, sync state.
Just one quick comment.
Sure.
So in ideal world, everybody switches off of not using devices for clock drivers, and actually switches to using struct device for a clock. We can delete the late init call if you can get to that point, right? It's more for legacy reasons. We need to keep it, right?
So why was it rejected? The one thing is that it calls clock enable basically during registration. And so clocks are going to be enabled again. It doesn't really do handoff in the sense that it touches the hardware. It's okay. The other thing is that it keeps clocks on for potentially a really long time because we don't know when sync state is actually going to happen, right? So we don't know when they're going to call that. It's kind of scary. The other thing is that it relies on devices to be used for registration, which not all clocks in the system are actually registered with struct devices because we have a early registration system for clocks where you can say, oh, I have a device node in DT and I need to register this, right? Because it's really early and it's used by like a timer or it's used by.
Just a quick comment. I think a lot of existing drivers abuse it, but they don't need to do it this way because there's like OF clock declare or whatever. They just use it because they copy paste another driver, follow the same method. Yeah. So ideally, we can convince them to move off of that and to start using actual devices.
Everybody has been already convinced. I tell everybody, don't use OF clock.
Okay.
Or whatever it's called. I don't even know what it's called because I tell them no one to use it. And the other thing that this problem is that we increase the software enable count with this approach, and that could be a problem because somebody may actually call clock disable twice, like from a driver, and they would never know. So we'd never find it. Right, so that's that problem. Those are those problems. Then we have the most recent approach from Able, which is do basically the exact same thing, but don't call clock enable during registration, and allow that sync state callback to be like general. And so it could be somebody else. It could be like a wrapper, or you could call it like something else before or after. It depends on what you want to do. All right, so this is basically the same. The rejection reasons are pretty much exactly the same, but the other thing is that it doesn't really do handoff at all in this sense because it doesn't really enable it. It's bad. We don't want to turn things off in the middle of the system. And the other thing it doesn't do is it doesn't really deal with that issue where, like, if you have the clock registered in one device controller or one struct device and another one, and that one never probes, like, we're going to disable a clock in the middle of the tree, and A is going to be turned off and B is going to die. So, like, sync state really didn't work there because we would still disable something if it never probed. So I went way back to the initial approach from Mike Fiquette, which is like, how can we do this? And it was done in like 2013, this past series, or maybe 2014. So the idea from Mike was to, like, let's do this all in software, basically. There's no sync state, it didn't exist back then. And what we should do is we should just like say, oh, when this clock is registered, right? If I've set a clock flag, like a specific flag in my driver saying like, then it says like, turn this clock on when you enable it, or turn this clock on when you register it, but don't actually touch the hardware. So we're gonna just increment the count, the enable count in software, and then we're gonna basically clear that flag so that the next enable doesn't matter. So this keeps it on basically until the first consumer of the clock gets a clock and enables it, and then doesn't really care after that. So like if a clock is shared between multiple drivers, it's not gonna do it. I think that's, yeah. So why was this rejected? Well, we required everybody to like say, oh, I gotta set this clock flag, which I mean, kind of everybody would have to set the clock flag if they want to use the feature. And the other thing is that it didn't really check the enable state like by reading the hardware. It just assumed that if you set the flag, it must have been on out of the bootloader, which is not always true. So now we just get the brainstorming. I guess we can start the discussion because I've wasted 8 minutes.
Hey, would you mind going back to the slide for the one I proposed? Yeah, right.
Okay.
So the main thing that I think Abel was trying to get around was the fact I was calling enable on an already enabled clock, and knowing the specific hardware issue or like the hardware behavior, that hardware just didn't like it. If you write to the enable register again, under some instances it wouldn't like it. To work around that, we just need to kind of combine, like set the handoff flag so that we don't call enable again for. So basically kind of need to add that kind of thing into my patch so that we don't enable if a clock's already enabled. That's one. Right? So that kind of solves this issue. And then the other part about, where the ref count, we can implement it a different way. We don't have to do it through ref counts. I can add another flag to say, look at the ref count, but also look at this flag. If this flag is, it's like a separate ref count, if you will. That's kind of what I would propose. So that should take care of every issue that you've registered here, and it should work. I just haven't had the time to get back, and you responded to my patch like a while ago, and I didn't send another patch.
So I think I have some brainstorm here. So we can just talk about what other people do real quick if you want to, or I can skip this. Basically, regular framework doesn't do anything like this. They read the hardware, they see if it's enabled, and then they have like a DT property that says like, oh, it's enabled out of the bootloader, and then they wait 30 seconds after late in it and just turn off things that are unused. Right? Nothing has changed. And interconnect has this, uses sync state, and actually like scans the entire DT, counts how many interconnect providers exist, and then says like, once every interconnect provider calls sync state, now I start doing stuff. I start turning things off. All right, that's the other approach. And what I want to do is I basically want to just delete the code. That's my plan. So I really want to just basically say, give everybody what they want, which is everyone sets clock ignore and use anyway. So I don't know why we're doing this. We should just make it set to true on the command line and just make a config option to do it, so that no one needs to, play games here.
Meaning you leave them enabled, right? Basically.
Yes.
Okay.
So the problem for this is that we're going to basically not save power.
Yeah. So quick on one other thing you mentioned in my patch series, which was later addressed by another patch, is people are complaining, hey, sync state never comes in my hardware. I want to turn them off. Don't wait for sync state. And then some people do want to keep it. If you actually go back to one of your earlier slides, I think the background slide, the requirements you have, two of them are actually kind of conflicting requirements. Not from, this one, that one. Right? First bullet is saying, I want to keep it on. But the last one is saying, don't disable if you don't have a driver. Right?
Right.
So there's a kind of conflicting requirements. It's going to be based on your platform or your board. So that's like right now is a runtime command line. You can say, if you don't want to wait forever for sync state, you can set a timeout for it.
Yeah, so I think.
So by default, we should never turn off. But if somebody's like, you know what, don't wait forever for sync state, just turn it off anyway, then they can just use that flag and it's done.
The clock framework is like very well not prepared to understand what to do here, right? It has no idea, and like using late in call doesn't work. We know.
100%.
Right?
Also, when all of them are modules, late in call is completely useless because you're registering the clocks way after this is all done.
It does nothing. What I can tell. This basically just makes things worse.
I'm fully okay with you deleting it. I can try to fix up my patch to address his concern and your enable count concern, and then I think that should solve it all.
If he removes the late init call altogether, we don't need to care about that. We only care about the disabling the clocks from the provider, basically. I mean, we still have to do that.
No, we'll need sync state for sure. The point is, what do you do about late in call? We can just delete it. If it should be fine. Deleting late in call doesn't solve your problem.
At least we don't need the clock disabled and used anymore.
Sure.
I think a lot of people's problems are
Only 1 minute left.
a lot of people's problems are that they don't want disabling unused clocks at all. And that's what people keep approaching the mailing list with, is saying, I don't want to do this. How do I not do it?
What about the people who do want to disable unused clocks and it works fine for them right now?
Right. Who are they? Just you.
Who are you? What company?
So what I'm experienced with is the all-winner platform, where we have clock drivers that cover all the clocks, and we haven't needed to use clock ignore unused in a decade because everything is fully modeled.
Okay. Yeah.
Mike. So are all your clocks available at late init, and has all the clients probed and consumed their clocks at that time?
No, but the drivers would re-enable any clocks that were disabled by the disable unused clocks when the drivers actually do probe.
Okay.
All right, so the next presenter will be Rui from Intel, and he will present remotely.
Can you hear me?
So, yep. Okay, you find your slides. PMD, right? Oh, PMD. And I'm going to give you the presenter, and just a minute. Oh. Oh yeah, okay. All right, so you should be able to present now.
Yep.
Just try slides. Okay, good. All set. Thank you.
Okay, thank you.
Yeah, floor is yours.
Yeah, let me close my camera for better audio quality. Okay. Hello, everyone. My name is John Ray. Srinivas and I work for Intel. Today, we will talk about the Intel low power mode daemon on hybrid CPUs. In this talk, we will first introduce the concept of low power mode on hybrid CPUs, and then the Intel low power mode daemon we implemented. And in the end, we will talk about the challenges we have. Some of the challenges already have solutions, but we haven't get them upstream yet. Some of them are still open questions. And comments are welcome. Okay, some background. On Intel hybrid platforms, there are multiple CPU types within the same processor, and different CPUs have different power efficiencies. So in some scenarios, if we run tasks on the set of most power efficient CPUs only and leave the other CPUs idle, power save can be achieved. This is what we call low power mode in this talk. On Intel hybrid platforms like Alder Lake and Raptor Lake, these CPUs can be eCore CPUs. And on Intel's latest hybrid platform named Meteor Lake, we can even get non-linear power saving because of its hardware design. So let's go to next slide. Okay. Compared with previous hybrid platforms like Alder Lake and Raptor Lake, which have P cores and E cores, Meteor Lake has 3 types of CPUs: P core, the performance core; E core, the efficiency core; and L core, the low power E core. P core and E core are located in the compute die, while the low power E core, the L cores, are located in a separate die named SoC die. Then, in scenarios like local video playback or some other partial idle workload that can fit in the capacity of the L cores. If we place tasks on these L cores and keep the SOC die active, the whole compute die are all idle, and the whole compute die can reach a low power state named DC6. And in our measurement, we do get power gains by doing this. For this purpose, we implemented a user space tool named Intel Low Power. The tool has been released in GitHub in the link here. As shown in this diagram, on the left, for the blue boxes, it reads the proc state to get the system utilization and CPU utilization. It also takes firmware hints from the kernel Intel HFI driver. And it also takes input from other user space applications like ThermalD and GNOME power setting. And based on this information, it makes decision to enter or exit the low power mode. In low power mode, to keep the other CPUs in a quiescent state, we need to migrate IRQs and tasks to the low power CPUs as shown in the boxes on the right. For IRQ placement, when IRQ balance is running, we talk to IRQ balance via socket message. And when IRQ balance is not running, we program the proc IRQ files directly. For task placement, we leverage C group to do this. We'll give more details in next slide. Yeah, as we know, C group CPU set controller allows restricting tasks to certain CPUs. In Intel Low Power Mode daemon, we support two different solutions. The first one is to change the systemd C group CPU sets to low power CPUs. This helps running restricting the user space tasks running on these CPUs. The second solution is to create a C group isolate partition and isolate the CPUs that should stay idle in low power mode. In our experiments, the C group isolate partition is the better choice because the other CPUs are more quiescent with no kernel threading running. But still, there are some challenges. Okay, the first problem we found is that when in low power mode, the isolated CPUs are idle. But scheduler still treats these CPUs as ordinary idle CPUs and use them for idle load balance. This is a waste of power because the isolated CPUs are detached from any scale domains. So they are just wake up from idle, find nothing to do, and go to idle again. In our experiments, we see that the isolated CPUs are woke up around 3,000 times in a 60 seconds run. I have posted a simple patch to fix this. The idea is that when do idle load balance, ignore any CPUs with no scale domain attached. This covers the CPUs in isolate partition case. So currently, there are some discussions about this patch, but we haven't pushed this to upstream yet. The second problem is that we do observe some unbound work queues run on CPUs in isolate partition. And good news is that I happened to find a patch set from Wyman Long when I was writing this slide. It seems to address exactly the same issue. I have just confirmed that the problem is gone with this patch set on top of latest upstream kernel. The third problem is that Srinivas observed that timers fail on the CPUs in the isolate partition. And for this issue, the timer patch series from Anna helps because the timer can be pulled by the low power CPUs then. Besides the challenges we had with C group isolate partition, there is another problem. Intel low power daemon detects the low power CPUs automatically. Say it chooses 4 E cores in one E core module on Idle Lake and on Rapid Lake. But on Media Lake, we have troubles detecting the alcohols. As shown in this in the slide. Yes, as shown in this slide, the most straightforward way to detect the alcohols is to check the cache topology, because alcohol does not have L3. However, current kernel cannot handle asymmetric cache topology, and the cache CCFS is missing on Media Lake. Ricardo has a patch theory to fix this, but this has not been upstream yet. Okay, so the Intel low power daemon put a system into low power mode to save power, but at the same time, it must exit the low power mode in time when the tasks don't fit the capacity of the low power CPUs, and this is for performance concerns. So response time is also critical. The fourth challenge is that as we monitor the system and CPU utilization to make the enter and exit low power mode decisions, this is done by polling the proc state. There are some firmware hints, but they are mostly tuned for Windows. So we are wondering if it's reasonable to have something like utilization threshold and deliver an event to user space when the utilization is changed. The second problem is that for IQ placement, talking with IQ balance via socket message takes time. It may even take hundreds of milliseconds to finish, longer than everything else we do during this low power mode state transition. And when IQ balance is not running, we need to handle a large number of IQ proc FS entries, and this also takes time. So we are thinking if there is a smart way to do this. Say, is it possible for C group isolation handle IQs at the same time? Yeah, this is the main slides I'd like to talk today. There are some backup slides, but I won't talk about them given the limited time. Yeah, and questions?
Vincent?
I have a question. Can you guys hear me?
Sure.
Cool.
Yeah.
So you're doing this on Intel hybrid machines, right? You have performance and efficient CPUs. So isn't it about time that you guys try capacity-aware scheduling, enable the CPU asymmetric capacity feature, so give like your efficient CPUs a little bit less of capacity and do the CFS wake up through the capacity-aware scheduling path? I'm not talking about energy-aware scheduling because you guys don't have
Yes.
OPPs.
Your question is clear. Your question is clear, and the answer is no. Okay, and the answer is no. And the reason the answer is no is not because of hybrid, it's because of turbo, and it's because of hardware P states. The way our hardware works is we don't know what the capacity is in software. It's done in hardware.
Okay, but isn't this related to what Vincent just did to have like a common single capacity reference? I think he was highlighting the fact that we have to have it because of stuff, for instance, like turbo states in x86. And like I said, I'm not talking about energy-aware scheduling where you need an energy model with different OPPs. I'm talking about
We're talking strictly capacity, not energy model.
Exactly.
Energy model is a whole nother disaster, right?
True.
The first disaster is capacity, and it's more important.
Okay.
So, say on Alder Lake, which is shipping today, we get Alder Lakes with the max guaranteed frequency is 800 megahertz, and the max turbo frequency is 5 gigahertz. So you can know your capacity is 800 megahertz, but it might be 5 gigahertz. That's a big difference. And the only way we can really know what the capacity is if we measure it at runtime and we run out of capacity. So you could say, hey, great, at this moment, I've got no idle time. I'm running at 2 gigahertz, so my capacity is 2 gigahertz. But milliseconds after that, or even microseconds, it could be something completely different. And it's not up to that CPU, it's up to a microcontroller, which is marshaling the resources that are available to all the processors in the package. And it happens too fast for the software to track. That's why we have a really difficult time with Linux's concept of CPU capacity on our hardware.
Okay. It's related also to Turbo 3, where when you run on Turbo level, then only some of the CPU can run, or only one CPU can run. Is this the case? And because this is would also not work then.
So there's 5 things that govern the frequency of an Intel processor and how much frequency you get. One of them is what you're referring to, which we call the turbo ratio limit, which says, hey, if you've got one processor, you can do this. If you've got 2, you can do another. But there's also, very importantly, average power. There's temperature, and there's current. We can't even see current. And there's something else that I can't remember. And we have at best only a handle on only one of them. We don't have the other 4.
Yeah. Anyway, so we ran out of time for this topic, and
Good question, though.
But yeah, it's a good question, and we can talk about it, later, or discuss it by email. So we need to switch over to the next topic now. Thank you, Uri. Thanks for the discussion.
Thank you.
All right. Interesting. All right, you're all set. So.
Okay, hello everyone. My name is Sudarshan. I work at Qualcomm in the Linux kernel development team. And the topic of my presentation is dynamic way of offlining DDR segments for power reduction. So the general idea or motivation is with increasing DDR sizes in the mobile systems these days, with more and more segments coming in, there's more power consumptions by this DDR. And if you have just a limited certain size of the DDR being used, for example, let's say 4 GB or of your 24 GB DDR, it kind of makes sense to collapse or offline some of the other segments that are unused to save power. And as you can see here in the trend, almost a decade ago, the DDR sizes for the mobile system was about like 4 to 5, so there wasn't much significant memory that you can offline. But these days, you have DDR up to like 24 and 24 plus GB. So there's good amount of segments that you can offline when system doesn't need much of the memory. So yeah, I mean, for example, if you have 16 GB DDR and then in your mobile system, if you're doing just light usage of the system, such as browsing, messaging, video, phone calls or such, and if you're using just 4 GB of memory in a 16 GB DDR, you can actually turn off the self-refresh current for other 12 GB of your RAM to save power over the DDR range. So that's the whole general motivation. And then as per this trend, with more and more increased size of the DDR, kind of makes more, saving memory on the DDR rails by offlining some segments makes more significant. So I think the two technologies we used for DDR offlining is PASR, and which is partial array self-refresh, and FRD, which is full rank down. So parser, in the left side, like, for example, if you have a 16 GB symmetric DDR, 8 GB rank 0, 8 GB rank 1, and you just offline certain segments in that particular rank, so it's like partial array or partial segment self-refresh, where other partial part of the rank has been in self-refresh and not other ones. So that is the password technology. And the full rank down is where you have the entire rank being shut down. So the entire VDD to the particular rank has been cut off. So there's a significant power reduction there. So these are the two technologies that we use to offline segments in DDR. So yeah, the basic idea is, if you have a larger RAM and if you're using just limited memory in that RAM, we can go ahead and then offline some segments to save power. So when do we offline and when do we online? We can offline when, let's say, there's no user interactions and there's a hint that there's no memory requiring app that's going to run. For example, let's say as simple as screen off or DOS. So DOS is more of an Android concept where if you have like 30 minutes of an activity, the system enters into DOS. It turns off the networking and other subsystems. So that's a good place where you can offline some segments. And when do we online them back? For example, if there's a screen on or there's a memory requiring app that's been running in the background, there's a memory pressure being built up in the system, and then the system kind of requires more memory, and that's when we bring the blocks online. So there's a feature called memory hot plug in the next kernel. It's same as the CPU hot plug, where we hot add and hot plug in and hot plug out memory, just like the DIMMs. So we use memory hot plug in the Linux kernel for software offlining, for page isolation and migration. So we use something called movable zone to host this offlineable region in a given DDR RAM. So the Linux kernel actually divides the whole RAM into different zones, such as normal zone, mobile zone, DMA zone, etc. So why we use mobile zone is it kind of guarantees that the pages can be moved. And why we need that is we want to make sure that if we offline a particular segment, there's no active pages there. And even if there are active pages, we want to migrate them out to some other place. So movable zone kind of guarantees that those pages can be migrated. So it's something that guarantees most. So we use movable zone for that. So there are different usage. Power save mode, if it's a UI user option, when you enable it, we can enable this memory offlining feature. And nighttime mode, where we know that there's no user activity there, and we know that there won't be any memory requiring apps that be running. And low battery mode, that's when you can also turn on your parser savings. And the normal mode, where even if the system is active, the screen is on, and you're doing some activity, but you are taking only few GBs of your memory, and then you can turn off some other segments. So that's another place where we can enable this feature. So now we know that we have this DDR technologies to disable to offline DDR segments in the hardware. But how do we know when to offline? How do we know when to bring them online? And how do we manage all those things? So that's the basically the memory pressure detection, and it's done by using something called as PSI, pressure store information. So this is actually the core of this feature. So pressure store information is something that's introduced in Linux 4.20 and onwards. So what PSI does is it basically just tracks processes stalling for a particular resource, such as I/O, memory, or CPU, and it tells what is the total amount of time that the processor is stalling, or what are the averages, what is the stall during these averages, or what are the average stall during this duration of 10, 60, and 300 milliseconds. So that kind of gives a short-term, medium-term, and a long-term trend of the memory pressure in the system. And the user space can query it by proc pressure memory. And PSI has this feature called PSI monitor, which can tracks memory pressure in a given window, and it allows user space to actually register to some events, and then it can wait using poll or ePoll events to know that if there's a memory pressure above a particular threshold. So this is something that the PSI monitor gives, and so the PSI monitor only activates when the process enters stall and deactivates when the process leaves the stall. So it's not like something. It doesn't sample every time. It only samples when the process enters in stall state. This is one of the slides I took from Suren from Google, describing about the PSI monitor. So if you see in the first graph, the blue line especially, when it has a stall, the sampling starts And in the given window, if the stall is more than a particular threshold that the user has been registered, it generates an event to the user space. So this allows, for example, if you want to get an event, if there's a pressure more than 100 milliseconds, you can register to that. And if you're doing a malloc or something, and the system is in the process stalling for more than 100 milliseconds, you'll get an event to the user space. So this can we kind of use to kind of monitor pressure in the system. This is a very simplified design graph here, a diagram here. So we have two user space services, the memory pressure detector and the power service here. The memory pressure detector, the whole job of that is to detect memory pressure going down, up and down, and it uses the PSI mechanism in the kernel. And this is purely written in C++. It's a native daemon. And the power service is it's a Java app that listens to Android intents such as screen off, screen on, and idle mode. And this kind of talks to a central entity or a central manager called as the parser manager, which listens to all the requests from these clients, the memory pressure detector and the power service. And the clients actually send requests based on priorities as well, like low, medium, and high. And the parser manager can decide. It's like a voting mechanism where it decides which service, which request to honor and which request not to honor. And the parser manager talks to the kernel space via sysfs writes and system calls, such as echo offline to memory 15. So that's more of a memory hot plug sysfs node. And we have a kernel driver that's registered to memory hot plug notifier, which notifies the driver when the memory is going offline and offline is done, and when the memory is going online and then the memory is online. And then beyond that, the kernel driver talks to other subsystems to do the actual hardware offline and online. This is more of a time graph here. Like when do we enter a parser and when do we exit from parser, meaning when do we do offline and when do we come out of offline. So after boot, we wait for some idle time, and then if there's no user activity and there's no memory pressure and if there's free memory in the system, we do a offline of low priority. And once we receive a screen off, we do a offline of medium priority, and then when the system enters DOS, we do a offline of high priority. And when we exit or when we online them back is when if there's a user interaction such as screen on or app launch, that's when we know that there's a memory requiring use case that could run. And whenever there's a memory pressure building up in the system, we try to bring the memory blocks online. So this is a graphical representation of the stalls. The black one is the overall stall, the memory stalls, or the processor stalling for memory. So you see that if we do an app launch, the stall kind of shoots up, and we have two thresholds here, like 200 milliseconds and 50 milliseconds. 200 is a critical one. So if the stall is more than 200, we know that there's it's a critical memory requiring app has been run, and we online make some memory there. And all the small humps over there, or the app usage where it uses some bit of memory. And once the use case is done and the pressure is down and it's been idle, system is idle in terms of memory pressure for about, let's say, 10 seconds. So that's a good hint or indication that there's no memory requiring apps, and that's a good place where we can trigger some offline and let the parser manager decide based on free memory in the system. So power savings, the more you offline, actually, it's the power saving is kind of linear. And I think this goes with the trend where the power saving on the DDR rails becomes more significant if you have higher DDR densities, like 24 and above, where you can do things like FRD, like you can turn off a full rank, or you can turn off more segments and for more power savings here.
One question.
Any questions? Yep.
1 minute. Okay. So what's your block size for the offline?
So that depends on the DDR like the geometry actually, but usually it's like 1 GB is the block size.
So so you have like 15 segments. So each GB is a block for.
Yeah, each GB is a block. Yeah. So that depends on if it's a Micron or Samsung DDR. So depends on the DDR geometry, but usually it's 1 GB is the block size.
And did you see any penalty when you online again?
Yeah,
Because
so
memory
we have made sure that
he has to rehash it, right?
Yeah, so we have made sure that the like the online time is like very low, like 200 microseconds is the latency when you get a memory pressure, and then when things are like online. So yeah, we have made sure that performance-wise there's no impact in terms of latency and everything. Yeah.
Okay, thank you.
All right. Thank you. This one.
Perfect. Thank you.
All right.
Thank you so much. Hello, everybody. My name is Sven, and I'm with Chrome OS Platform Enablement. So we make new Chromebooks, basically. So this is a overview of where in the big forest of power in Linux that I want to talk about. I'm going to zoom in on this section. It's going to be about idle states, sleep states, more specifically runtime idle. So before we continue, I have a little confession to make. We monitor dynamic idle states. Yes, we do. We monitor them and we track them. Why? Because they're important, right? So when we do platform enablement, we go through a journey. It's kind of a funnel. You start with like a big tolerance, and then as time goes on, it becomes narrower and narrower, and we have to track it. And you're asking me like, aren't you just tracking the power? Why are you also tracking the idle states? Well, they're important, even though, you can meet your, you can meet your power requirements. There could be, if you're not meeting your idle residencies, you could be leaving power on the table or idle power on the table, right? So they are important. You have to measure them, right? So what this talk is about is the system that we use to measure them is currently like a patchwork. It's organically grown. Some of the things, are in sysfs. Some of the things are in debugfs. Some things, are overlapping. Some things are not there at all. So let's start talking about CPU idle states. So on ARM, that's relatively straightforward. It's like wait for interrupt. The CPU is off, the CPU is on, or it's asleep. It's nice and binary. On x86, we have these famous C states. C0, it's alive, C2, C8, C10. We have all these different states, right? So then you can say, okay, the CPU idle driver should track the residencies in sysfs. Why don't you go and look there? You can see what they are. Fantastic. Except two big things. There's things, there's like C state emotion going on. So the CPU idle state driver can ask for a state, but the hardware isn't necessarily providing it. Excuse me. So it can do something different than what the driver is asking for. And that isn't reflected in the statistics. There's also a lack of atomicity, because there's like a bunch of sysfs nodes that you have to read for all the cores. And if you don't all read them at the same time, you take some time to read all of them, well, time moves on. And it doesn't all completely fit together. So we had instances where, we had instances where we didn't actually, we took a little bit of time to read them, and the C0 residency actually turned negative. So in Go, we had to write like Go routines to try and parallelize it and try to read them all together in CPU idle to kind of get a decent reading out of it. It was all very complicated. So moving on from these CPU idle states is module idle, right? So that's on ARM, that's like cluster, sleep on, sleep off. It fits really nicely in CPU idle, except that in x86 it doesn't, right? These are package C states. So that PC0, PC2, PC10. Now, these stats you can get through debugfs, or you can get them through vendor tools. Some people here in this room might be, familiar with turbostat, I suppose. And there's also ACPI LPIT going on. It is not so fantastic because we have different debugfs formats. They differ between x86 vendors, even kernel versions, it differs, right? Now, when you go look at the debugfs file, excuse me, you will see that PC0 is missing. And that, again, that's a bit of a problem because when you're reading that debugfs file, you know, you have to reference it against the time base. And the time base that the debugfs file gives you is not necessarily the same as the one you have. So it invites all kinds of rounding errors. It invites all kinds of systematic errors that we ran into, actually. So also what happens here is because these taking these through debugfs doesn't work very well. Now we use like the turbostat way, and we go and we read them straight from raw registers, right? Now it invites duplicate implementations because we have an implementation for Go, we have an implementation for Python. There's probably a Rust implementation there somewhere that I've overlooked. It's probably there. So now we go to the SoC themselves. If I understand this correctly, this exists on ARM. It fits very nicely in GenPD, if I'm not mistaken. On x86, that's an S0IX state. Currently, it goes from 2.0 to 3.4. So again, there are different levels. Again, we have to go through debugfs or the vendor tools. Going through debugfs, you know, it's also not so great because again, it differs between x86 versions, vendors and versions. The total time also is missing from debugfs. Again, it invites accumulating systematic errors. And again, same problem. We have like duplicate user space implementations that are invited by reading those registers. Now we get to S2 idle, right? So with S2 idle, what we do is we repurpose these dynamic idle states to implement a static system idle. So the idea is that we get comparable power savings and, you know, lower static resume latency by doing that. So the residency stats, they are read historically through like a patchwork of vendor-specific paths. I believe recently Mario Limonciello, he landed an improvement that actually happened before this abstract was created. So thank you very much for that. But there are quite a few gaps here, like how deep is the deepest reached idle state, you know, the main thing that we see is we go to S0IX, we'd go to like suspend mode, static suspend mode, and actually we didn't get there. You know, either it hangs or it comes straight back and it didn't work. And then of course you have to figure out, okay, why didn't you get there? What was the dynamic idle that you couldn't reach, and why couldn't you reach it? And something like that is not so easy to determine because it happens in the field a lot. Like, okay, when it happens during platform enablement, we can catch it, we can debug it. Then we start seeing it in the field. And how do we debug it? Well, you know, Intel throws a bunch of bits at us. So we get like a bunch of bits, fantastic. We send that to Intel, we say, hey, what do these bits mean? And we get something back, but it's not really scalable. We would like it to be a little bit better. So unfortunately, my talk is like very long on questions and very short on solutions. So number one question is the current patchwork we have. Do we want to change anything there? Do we want to make it like more generic? Do we want to make it more standardized? Do we include some sort of topology, you know, so that we have like one system where you can read all these states and, you know, you really know what's going on without all these interesting calculations you have to do. What about the special relationship to S2 idle? Is there a possibility there to add something that if your static suspend doesn't work out and you didn't enter some runtime idle mode, you can actually see by looking at that particular subsystem? And again, also the LPIT, how does that fit in? That's what I wanted to discuss. And I didn't just want to throw a patch set onto the mailing list. I thought it was far preferable to discuss this with you highly esteemed gentlemen here. Yes.
You ask a lot of questions.
I do.
What measurement interval do you care about? Like on those graphs, I don't think there was a y-axis. It matters. So it's possible to go faster and faster such that you'll notice the skew more. If I ask for how idle was I in the last half hour versus how idle was I in the last microsecond, and it takes me a microsecond to read the counter, then one has a problem and the other doesn't. So depending on where you turn that knob, it's going to make it practical or impractical to measure.
I see.
When I wrote turbostat, the default measurement interval was 5 seconds. Sometimes it's used on the millisecond range today. But errors such as the one you referred to will creep up. You'll be like, well, how do you count C1 time? Well, on some processors, it's the non-idle, it's the idle time which is left over because it's not in any other counter, and you add those up, and it's possible to go negative, right?
That's right.
And so my question remains, what kind of granularity do you need? Because that will dictate the kind of solution you need.
So what we do is we look at various system loads and various use cases, and we're talking like 30 seconds, a minute, 2 minutes, 5 minutes, something along those lines. And we want to see every couple of seconds. Ideally, we want to see what the residency, what the idle residency
seconds
is.
should be easy. Should be quite easy.
Easy through what mechanism?
Turbostat's pretty happy on the multiple second granularity.
Turbostat reads the raw registers, right?
It does. Yeah.
So for that, the thing is, we then implement it in user space. We have multiple implementations. Also, we have big tables because.
Let me address that part too. So it's been, in fact, we've had a prototype. Basically, what you want is atomic read of multiple counters at the same time without a system call for each one. And I think what we really want to do is extend perf to do that for us. So I can give perf a list of counters and say, give me all these in one system call.
Yeah.
That's really the right way to do it. And then you can put whatever tool you want on top of that. I think that's the right solution today.
That sounds logical.
Yeah.
And that would replace some of the counters and some of the stats we have in.
It would
in
replace
SysFS,
the individual
debug
calls to the MSR driver in our case. Yeah. In fact, I mean, we already use perf for some things. It's just that it doesn't do this. We have to extend perf to do this.
Yeah, exactly. Exactly.
And reads are pretty fast. Reads in Linux are really quite fast.
Yeah. Is perf, as a subsystem, is it quick enough to do, capable enough to do these things? You believe?
Yeah, for what you're talking about, yes. Very much so.
Interesting. Excellent.
Now that said, some counters are just slow counters in hardware, and if you touch one of them, it's like, hey, see you 3,000 cycles later. That happens too. So you have to be aware of that. You could ask for a counter that's an expensive counter, and then, what can you do? Can't go any faster than hardware speed. Some of them are fast, some of them are not so fast.
That's right.
Like that SRIX counter in the LPIT, that might be a slow counter, right? That's out on maybe another chiplet. Yeah.
Yeah, the LPIT counter is a good example of the fragmentation we have, right? Because it's there on Intel, it's not there on AMD.
Well, at least ACPI enumerates it. You either
Yes.
have it or you don't.
Yeah.
The hardest thing you've described is how to debug when you don't get SRIX. I concur with that. In the lab, we struggle with that in the lab. And so if that fails in the field on a system you debugged in the lab, it's like, now what? There are tools you can get from us to run on that, but it doesn't mean that they're available in an end user system.
Exactly.
They're available to you, but maybe not to that user.
Exactly. The thing is, we do tests in the lab, obviously, but once it goes out in the field, the scale becomes much bigger, and we see a greater granularity and a larger amount of failures, and we can deduce much more from that potentially, if we have good visibility of what exactly is going on, which is not so easy to do with a bunch of bits that we get from syslog or.
So I would say over the last 5 years of SROIX evolution, the trend is good. It used to be much more fragile, and now in current chips, it's not so difficult to get very good. You may even have runtime SROIX in PC-10 residency, which before was unheard of. Today, it's like, holy smokes, if you have a self-refreshing display, you're in PC-10. It's like that was impossible like 2 generations ago. So that's the trend is good, I guess. At least from my lens. You may have conflicting information, and I respect that if that's the case.
Sorry?
Hallway track.
Yeah, hallway track.
Oh, I thought you were saying something.
Yeah.
Hallway track. Awesome.
Yeah, I just ended the session.
Out of time?
Yeah, out of time.
Thank you so much, everyone.
Yeah, this is it. Thanks for coming. Thanks for content. Everyone who participated, and hopefully see you next year. Thank you.
We have tomorrow to spend at 2:30. Talk. Yeah. And so I'm going to hopefully have you hold the mic because A, any questions will come right to you anyway. B, if I forgot something, you'll just speak up. So I'm hoping that you're more than a passive participant in that session.
What time it is,
I think it's 10:30. Well, not up. It's before lunch. It's like in that. It's after the break, but before lunch. Okay.